Good morning, everyone, and good afternoon, good night, regardless where you're located. Hello, and welcome to the first Data Science Summer School organized by Hertie Data Science Lab and Data Methodology Center at the Scripps Cluster of Excellence. I would like to thank our funders, the Scripps and the Stifterverband, for their generous support. And because without the support, the summer school wouldn't happen. And I'm extremely happy to see you all here today, both on Zoom and on the parallel stream on YouTube. And I would like to note a couple organizational and technical details. If you're in the Zoom meeting, you're all muted and your cameras are off upon entrance. Please do not unmute yourself and do not turn your videos on unless you have a question. Really ask you to put questions in the chat. That way it's going to be easier to handle the questions for the instructor and the TA. However, if you really want to speak up, you can raise your hand, and then whenever there's going to be a good time, we will let you speak and ask your question. If you're in the parallel stream session on YouTube, you can leave your comments and questions in the live chat, and we'll try to handle them as well, either by responding ourselves there or directing the questions to the instructor and the TA. And I should remind you all that the Zoom session is being recorded, and I'm thanking you in advance for following these rules. And without further ado, we shall begin with the sixth workshop in the summer school series, and the topic that I'm personally really excited about, images data. And let me introduce you Dr. Michelle Torres. She's an assistant professor at the Rice University in the United States who specializes in political methodology and political behavior. Her research focuses on making statistical and computer science methods accessible to political scientists. She also develops and applies innovative and rigorous tools to achieve a better understanding of social issues, especially in the fields of political behavior and public opinion. Michelle, the floor is yours, and you can share your screen now, and thanks.
Thank you so much, and hi, everyone. Welcome to this session. I am really humbled that you decided to join us to learn a bit more about image analysis. I will share my screen in a second. Meanwhile, I'm going to tell you that I'm actually in Berlin, even though I live in Houston. I'm actually in Berlin, like visiting family. And Berlin received me with a beautiful cold. So I might be coughing a bit during the session, but this is the advantage of being offline, right? That now we shouldn't worry about this. Just give me 1 second. Okay, let's get to this. Perfect. Can everyone see my screen? All perfect?
Yes, it's perfect.
Perfect. Okay, so I will start today with a bit of the motivation for image analysis. Olga already said everything about me that you need to know about my research, but I am a methodologist at the Department of Political Science at Rice University. And I mostly focus on computer vision, computational social sciences, and causal inference. And my substantive interests lie in political behavior, public opinion, and political communication. In particular, all of my research can be summarized in the question of what role do images play in the political communication process. I am very interested in knowing what images from political events tell us about them. I am interested in how they are generated, how political actors use them strategically or not for their purposes. And I am very interested in how also they affect political opinions and attitudes towards social events. So I studied the different parts of this chain. And in particular for today, I am going to tell you about a few tools and techniques that we have to analyze the content of images. Because the problem is that we live in a visual world where we are bombarded by images all the time. And even though it would be great to have very deep qualitative content analysis on the images that we see about the political world, in reality, it would be impossible nowadays, right? Like if you think about social media, if you think about newspapers, videos, etc., it's just an amount that we can't handle. So that's the reason why we are like asking the computers to help us a bit, not replace us. That's a very important thing that you need to keep in mind even before starting this seminar. But they are going to help us to classify and to analyze a bit of the material that we're going to study. So, and there are extra motivation beyond having a lot of images in the world. They are powerful, right? Like they provide extra information that goes beyond text. They have these amazing quality of activating emotions and other cognitive processes. And they have this feature, this property that they let you, like, that you have like a full picture of what's happening, ironically. And then you have this saying of like, see to believe. Once you see an image, you are more likely to believe something, you're more likely to recall it, to engage with it, because it's a representation or a better representation of reality. So all of these things really help with recall and engagement of the information about the political world. The other thing is that images are kind of universal. Of course, I'm like putting some quotations here, but if you compare them to spoken languages, the images are more general, right? Like you can have an image of a protest in Ukraine, and you have an image of a protest in Spain or in Mexico. And of course, there are going to be different styles and different content, but you can actually start analyzing protesting that way without caring too much about what language is spoken in these countries, right? A thing that I am particularly interested in is that visuals are friends, right? Like something that I see in my research a lot, which deals generally with standard or traditional media, is that newspapers use images in very different ways. And most of the time they are using exactly the same text that comes from newswire sources, but they have actually some flexibility in choosing what kind of images they want to pair their articles with. So this idea of like, what do you want people to see from the images, it's something important, that it's also an interesting element of images that makes us want to study them more. And of course, they offer new possibilities for measurement, right? Sometimes it's really hard to measure some things, but in these times where technical capabilities and computational power is like there for us, we can think about using images to measure and discover new things that otherwise would be difficult, right? Like using Google Street Views to measure ethnic visibility in small communities, natural disaster and prevention and evaluation. That's something really a hot topic in Houston with all the hurricanes and floodings. State capacity based on roads and in like the connection between cities. It's just a wonderful source, or a wonderful data to collect, to think creatively, with a lot of creativity about how to measure the things that we're interested in. And to analyze these images, there's this field in computer science, which is computer vision, that is focused on teaching the computers to see. Again, with the idea of processing large pools of images, and with the objective of increasing consistency and reliability and decrease biases, right? Like humans tend to like see one thing and then they get tired and start making mistakes when they are coding, or sometimes they forget what the rules for coding were, and those things don't happen with the computer. You can give them a million pictures, and if you set very clear rules about how to code them, the computer is going to do them in a very reliable way. I am putting an asterisk here in decreased bias, because we generally think about bias in the way of like, oh, a Republican or a Democrat are going to code images differently, or they are going to perceive subjectively images, and the computer is not going to do that. But when we're training the computer, we as the researcher coding and programming these algorithms might also import our own biases in them. So that's something that we really need to keep in mind. The computer is, yes, follow a set of rules in a very systematic way, but if those rules are biased, then the computer is going to be biased as well. And there are multiple examples that I'm sure you guys are all thinking about right now regarding biases in artificial intelligence. And finally, the other objective is, well, computer vision tries to train the computer so they can help humans to see and discover. But that's also something that I'm putting an asterisk, because even though, yes, the images are going to like look at thousands of the computers are going to look at thousands of images and find patterns and find clusters and tell you something about them. At the end, they're not going to discover anything particularly new that you have missed. If you as a human can't code or can't find something in the images, the computer is not going to do it for you. You always, and I'm going to put a lot of emphasis on that throughout the entire seminar, you always need to remember that you are teaching the computer. So whatever, like all the mistakes that you have, all the biases you have, and all the things that you are not seeing or that you're seeing is what the computer is going to learn. So we are not, they are not exempt from all of these problems that humans have as well. Okay, so let's go back to this idea that we're trying to teach the computer how to see. This is a very hard task. I have a 6-month-old baby, and partly for my research and partly because I was very interested, I started reading a lot of papers about how humans learn to see. And it's a fascinating world. Like if you have the time and chance, read those papers about how babies develop skills to see. And things that, of course, now we as adults or as like older children, when we do in a very natural way, like object tracking, it's a very hard task that you need to learn. But humans are incredibly good at doing those things, right? Like even though they are hard and they require some practice, in months you can already be incredibly good and proficient at seeing. But computers actually struggle. And the thing is that computers are great at following instructions reliably, right? If we want to identify Putin in a set of images, because we're interested in like spotting him or finding him in a pool of images, we can actually give the computer a lot of instructions of how he looks like, right? Oh, he has blue eyes. Oh, the distance between the eyes is this. The shape of the nose is this. He has a forehead like that, the hair color, etc. And this is mostly what we generally do when we are programming and when we are doing or like using other algorithms. We like basically give a full code book of like what to find. If you think about a dictionary based text analysis method, is like, okay, look into this corpus and find these words. These are the instructions. And with images, we can still do that. But the problem is that there are multiple ways in which Putin can appear, right? And the computer then, it's really bad at making inferences when those things happen. So I put a picture of Putin here and you were able to identify it. If I put this picture here, you will still be able to identify Putin because of all this, the symbols around him and like the context, right? But the computer will totally, like if you just gave it a set of instructions regarding how his face looks like, the computer will fail miserably at inferring that Putin is here. So we as humans are able to infer a lot of things from the images based on the context. If you put a cat and then cover half of the cat with a curtain, you're still going to be able to detect that it's a cat. But if you don't account for all of those things and you don't teach the computer all of the possible scenarios where the cat can occur or can be appearing, then it's going to be a very hard task for them to spot it or to classify it, right? So it's not a trivial thing to do. And that's the reason why we need to think very creatively about what tools and what methods we use for analyzing our images, because giving a set of instructions is not going to be feasible. And another thing, this is a funny example that probably you've seen, even with very sophisticated and cool methods, computers are still not the best at seeing like us. So there's this challenge of classify whether it's a Chihuahua or a blueberry muffin, and the computer still makes a lot of mistakes when determining if it's a Chihuahua or a blueberry cupcake. So just so you have that in mind as well. So for today, we're going to review some of those creative methods to analyze images that will help us. Again, they are not bulletproof, but they are going to help us a lot to understand them and to classify a lot of images. I'm going to start with some image basics. I'm sorry if they are too basic. Please like ping me in the chat if you think that's too basic. And I'm going to talk about some software and computational requirements, not precisely for today. We're going to do some of those things in practice, but when you are ready to do your own project and analyze your own images, what you need to do. We're gonna talk about basic features of images, in particular color statistics for this class. We're gonna talk about the bag of visual words for unsupervised classification, and we're gonna talk about the very popular convolutional neural networks, which is arguably the most popular and well-known tool in computer vision for image classification. In this part, we're going to talk about I'm going to give you the overview. I'm going to talk about the structure and the implementation, and we're going to have an application. But my idea in this seminar is also to tell you that all of these tools have a very strong statistical and mathematical core. Some people tend to think and tend to talk about them like they are black boxes with magic, and the ways in which they operate are basically unknown. But in reality, there are like a lot of equations and derivatives behind. So it's yes, it's magic. It's the power of statistics and the magic of statistics that it's working behind the stage. Okay, so hopefully I will get that message through you when talking about this. And then we're gonna talk about other miscellaneous tools that you can use right out of the shelf, like the Google Vision API, which like lets you do some good things. We're going to talk about validation and diagnosis, and I'm going to give you some final warnings about the scope, the biases, and some unintended problems that happen when using these tools. And at the end, we're gonna use the Google Colab virtual machine to see some of these things in action. Okay. So the workshop material will be in my GitHub page and in the official website of the summer school. This is the link that we're going to use for the Google Colab notebook. And when doing your own projects, these are some things that you need to keep in mind to install in your computer. This page, the PyImage Search OpenCV tutorials, it's a fantastic resource for installing OpenCV from source. If you don't install it from source, you don't get access to like the full functionality. For example, certain descriptors are really important for the bag of visual words. So if you want to do that, you really need to install it from source instead of just using pip install, just so you know. So I put the links there and all the resources, but I'm also very happy to talk about them in the Slack channel, or if you have questions during the session. Okay, so before I start with the image basics, any questions?
Michelle?
Yes?
Will you be posting, or do you have the links that I can post in the chat?
Oh, yes, I can like just copy them now.
Perfect.
Okay, no, I don't see the chat here, but up here it is. Okay, that's the Google Colab. And well, and that's a PyImage Search link. Okay, right. Okay, sounds good.
Sorry, Michelle, Colab link might not be working. Maybe it's because of copy pasting. I don't know. Oh,
maybe. Okay, let me check it. So we're not gonna use it right now. Right before we use it.
Yeah, we're good. We're good. Sorry. Like I think there was just with copy pasting some issue, but we fixed it. So sorry about that. Yes, we're good.
Okay, perfect. Perfect. Let me, oh, the chat is now going crazy. Okay, sounds good. Okay, so image basics. So you probably know this, but an image is just a set of pixels, right? The pixel is the smallest unit that you can have in an image, and it's basically defining the height and width of a particular picture. When it's a grayscale image, a pixel is basically the intensity of light. So sometimes it's kind of counterintuitive when you see a value of 255 and it's a white pixel, but that means is 255 light intensity. So it's like the lightest that you can go. That's the reason why it's white, and 0, it's black. Okay, and when it's color, it's a color intensity of a color channel. And we're going to talk a little bit more about this in a sec. Images the way that we use it in Python and the way that we actually, not only in Python, in C++, in Java, in R, it's always like a matrix representation. So you have a grid with the height and width, right? And because each of these pixels is going to be a number with that intensity, you can now see how this is just a matrix. And this matrix representation is going to really help us to speed up some processes because matrix operations are computationally cheaper than dealing with lists or other types of vectors. So it's a really nice feature, and it's a really nice natural property of images. Grayscale images are going to be just one matrix composed of the light intensity. The numbers are going to be the light intensity, and color images is going to be an array with a matrix for each color channel. So as I told you, each pixel is telling you the color intensity of a color. So that's the reason why you're going to have 3 different channels, one for red, one for green, and one for blue, stacked together to form your image. Something that you need to notice in OpenCV that you're going to think that I'm crazy for mentioning it now, given that we haven't reviewed anything, but trust me, it's going to be helpful when you're going to do your own projects with image analysis. The color channel specification there is BRG instead of RGB. So sometimes it can be a really bit confusing. The origin of image is different. So when you see this image and this like matrix style and you picture it in your mind as a plot, we generally tend to think that this is the x-axis and the y-axis like in a normal plot, right? Well, in OpenCV, when you're dealing with them, the origin starts here at the top left corner. So then you start counting from 0 to the width and from 0 to the height in that direction. So that's something to remember, especially if you're cropping images or you are like doing some transformational stuff with them. And because we're going to use this library, or most programs or code that you're going to find online is going to use NumPy and OpenCV, you need to specify, or you need to remember that the specification of the y coordinates of an image goes first. So instead of putting X in the first part of an array, then you need to put Y. So you don't need to remember everything right now, but those are important notes that you need to have in mind once you're ready to dive into this. Okay, so we're going to talk about color descriptors. And this is just one fun feature that I find of images, just to give you an idea of a lot of things that you can extract from them. So that's the thing. You have a lot of pixels, right? You have a very multidimensional problem when you are dealing with an image. So there are many things that you can do to summarize what you're finding there. You can detect objects, you can get the color distribution, you can extract features based on salient points, you can do a lot of things. There are multiple ways of extracting features from images. But color descriptors is one of the most basic, but it's really neat. So I will show it in a sec. So I will go back to this idea that we have a challenge when we're dealing with images, and is that we have a lot of pixels, and they mostly make sense just when you analyze them in clusters, not in units, right? Like if you just see like a little dot there, it's not going to tell you anything about that image. So if you think about these pixels as potential covariates, for example, or as potential descriptors of the image, they are not going to tell you a lot, because when like they only acquire meaning when they are put together into a line or a shape or a corner or a particular object or texture, right? So you can't just treat them separately. So that's the reason why we're going to use image descriptors to characterize the content of an image. You can either do it globally, or you can do it locally for certain regions of the image. And again, you can then extract texture, shape, objects, etc. But today I'm going to focus on color just to begin with. A feature vector is going to be just a simple series of numbers used to numerically quantify the contents of an image or regions of it, right? So you're going to have a long vector that it's going to be meaningless to you, but that the computer is going to know what it's attached to in terms of like properties. So the color statistics, you can have two like basically methods. One is the channel statistics, which is very, very simple and very intuitive. Basically, you need to get some basic stats that you know, like the mean and the standard deviation of each color channel, right? So the problem here is that you will have everything separately and not jointly, but still some of these distributions of like the red color, the green color, the blue color in the image are gonna still be useful or interesting to see some patterns. Then on the other hand, you can have color histograms that really take into account like this joint distribution of colors. And you can have, for example, a 3D histogram of colors. You need to convert your image to a certain color space. Then the computer will compute a 3D histogram. And at the end, these histograms or these channels or these particular statistics like the mean or the standard deviation, you're going to concatenate them to get a feature vector. So again, this idea that you can just do something as simple as compute the mean and standard deviation of the red, green, blue channels. And if you put those 6 numbers together, that's going to be your feature vector defining that image. That's like the most basic thing that you can do, but it's still saying something about what you're finding in those pixels. And once you have these vectors for each of your images, describing them in a way that you define, then you can do many things to find patterns. So you can compute vector similarity, for example, you can run k-means, you can do some clustering algorithm to find patterns. And even though these things are so tiny and so small, you're still going to be able to be powerful enough to find some interesting patterns there. So this is a way of like computing vector similarity against some like Euclidean distances that you've seen probably since high school. So very, very basic stuff at the core of these methods, although they generally tend to sell them as incredibly sophisticated and shiny. So we can have with color statistics, for example, I basically just did that. Like I computed the mean and the standard deviation for the 3 channels in these images. And then I computed the vector similarity between these 3 and this one in the top left. And as you can see, this is the closest one in terms of colors. This is a little bit further, and this is the most different from it. So without a lot of fancy techniques, this is just with like simple matrix means and matrix standard deviations, we get some idea of like, yes, these differences in colors are definitely defining something in the pictures. This is, of course, not going to work for more complex questions, but it's just a basic example. You can also, as I said, use k-means, for example, in some of these vectors of statistics, of color histograms, and cluster your images and see how these clusters are behaving. In this case, I had a bunch of pictures of political propaganda. And when you cluster them, you see that, for example, cluster 1 is including all of this propaganda related to environmental issues. 1 got sneaked into the cluster number 2, again, because it's not super perfect. But like you also got the feminist ones here that tend to have red color in them. And this was just with like a vector of size 6 for each of these images. Okay, so that was the most basic thing that you can do. And it was just to, again, like illustrate how you have multiple features in an image and you can extract those features and define this extraction. Like there are no specific rules of what you can use. I think that's it's both a blessing and a curse in computer vision, is that you have a lot of flexibility to define what a feature is, what a characteristic. In text, for example, you have words, right? And you generally use words in your bag of visual words, in your document term matrix, or you use sentences, or like now with neural nets, you use embeddings. But you have some limits on how far you can go in terms of like choosing the way or choosing the tokens that are describing your text, right? But in images, you have a whole tool for describing them. Excuse me. And that's the reason why I talked about color descriptors, because that was one way. Now I'm going to talk about a slightly more complicated one, which is the bag of visual words, and which is in the middle path between the super basic color descriptor and the neural net that is defining features in a much more complex way, okay? And the bag of visual words is one of my favorite tools, because it's It's very simple. Computer scientists will even tell you that it's outdated because now neural nets and deep learning has taken over the field. But I think there are some really nice advantages of this method that are interesting for social scientists, because that's another thing that I want to talk to you about, and is that the goals between social scientists and computer scientists sometimes differ wildly, right? Computer scientists sometimes are really concerned about improving accuracy of classification by even a tiny little point, decimal point, right? And social scientists are less concerned about that. Of course, we care about accuracy. Of course, we care about how good our classifiers are, but sometimes we care about what's behind those algorithms, what's driving a prediction, right? Like if you think about a regression, you don't use regression just to predict the outcome of an election. Yes, some people do that and some people are interested in that, but most people are also going to be interested in what are the factors that are driving that election result, right? What are the factors that contribute more or less to a particular outcome that we're interested in real life? And sometimes all of the tools that we see from computer vision and computer science are not designed for that particular objective. They exist, but they don't receive this like the same level of attention. So that's sometimes our role as political methodologists, for example, to bring some of those concepts and really adapt them to what social scientists need and want, right? So that's the reason why the bag of visual words, you'll see in a minute why it's interesting. Basically, you can track a lot of the steps in the process. It's like very intuitive, and you can still get a lot of information about the steps that are leading to your final result, rather than just the actual classification label, and that's it, okay? So the bag of visual words is this tool that tries to emulate a document term matrix. If you are familiar with text analysis, you know that a document term matrix has the words, has it like the texts of interest in the rows, and the columns have the words that appear in those texts, and then you simply count how many times they're appearing in each of the rows. And we're going to try to do something similar with images. In this case, there are not going to be actual words or actual objects like, oh, look, there's a flag. Flag is one of my words in my column, but there are going to be patches of the image, like little, like think about if you have an image and you like cut it into little pieces and you like scramble them in a puzzle. These little patches are going to be the words or visual words that we're going to be using, okay? And the process of this bag of visual words starts with identifying key points, then extracting features from these key points. So this step, again, that we did with the color descriptors, we're going to do it with some gradients, and we will review it in a bit. We're going to create a visual codebook because unlike text, we don't have words or sentences to take as reference, right? We need to create our own tokens. And then we're going to build this image visual word matrix that emulates document term matrix in text. I see a lot of things going on the chat. So Alex, do you think there are important questions that I need to answer right now?
I mean, the main question is whether we can consider images as structured or unstructured data, and given that they can conform to a matrix of numbers.
Yes. Okay. Yeah, that's a great question. I will still consider them unstructured data, just because it's just too much to handle. And again, like this flexibility of defining them in multiple ways really makes them, so it doesn't mean that you can't put a structure on them, but it's always going to depend on how you define it. And there are going to be, even in a CNN, all the filters that you're going to use and all the ways in which the architecture is manipulating or operationalizing some of the pixel patterns there, is going to be much wider than what we generally have in normal data settings, like, I don't know, countries going to war and certain covariates explaining the economic and social context of those countries, right? So it doesn't mean, like, it's true, like, because it's a matrix, and we can even think about it as a very particular, already structured data set. But again, because all of those numbers alone are not going to mean a lot, and then we need to impose our own structure onto them, then I think I will still call them unstructured. Hopefully that answers the question. If not, we can talk more about that at the end. Okay. So key point detection is the first step that we're going to have in our bag of visual words. And here the point or the objective is to identify salient regions in the images. So edges, corners based on pixel intensity changes. Why are we doing this? Because all of these points, well, here in this case, I used the fast Hessian, which is fast and scale invariant algorithm to detect key points. And here I already plotted them in this picture. And the interesting thing, as you can see, is that these key points are aligning along the edges of very salient features of the image. And these features, if they are salient, it means that they are saying something about the content of the image. So you can, like, these edges are aligning also along the objects that you can find them, and those objects are telling you something about the overall content and message of the image, right? So in a way, if you still want to compare this to text analysis, this is basically like a stop word or like a stop word removal stage, where you don't care that much about the background, for example, but you care more about the things that are happening. And you can still vary, like you have some hyperparameters that you can vary to probably include a bit of the background. For example, if you are interested in whether things are happening at day or night, or you're interested in the background. But in general, the idea is that you just focused on more salient elements of the image to avoid using things that are not going to inform your classification that much. Okay. And the picture, the key point detection, this is like how with stats and math, we can get to them. We can identify them. As I said, the fast Hessian, it's this algorithm. Like there are many key point identifiers, but I am using the fast Hessian because it's really computationally cheap. So even if you have like live applications, you can do it, and it will perform really optimally. And the process to identify the key points is you're going to scale or smooth the images to create octaves, right? Like this is basically just to really blur the images and add some like noise in a way to really identify those that are those points that are salient, and not only like a stain or something that it's not part of like really of the image as a key point. And to do that, we're gonna use an approximation of a Gaussian second order derivative filter. So this sounds very sophisticated, and I'm just gonna put it there, even though it's overwhelming. A lot of, one of my advisors used to say, a lot of Greek letters are really overwhelming. But in this case, it's just to show you that we are gonna have a matrix with some derivatives. And these derivatives are actually very computationally expensive. Generally, when you have images and you need to slide this matrix along an image, this could take some time. So the thing that makes fast Hessian so fast is that instead of using this matrix with derivatives, we use an approximation of these derivatives. And this approximation, which has like really basic operations, like just multiplying for 1, for -2, or for 1, actually make the process incredibly fast and still very efficient because it's approximating this result. So again, you have an image, you have some of these filters, and you're gonna slide those filters across your image, and you're gonna estimate the dot product of that filter in each region of the image. What intuitively this is doing is that if you have a dot product that is really high, for example, for this particular filter, it means that you are finding this particular pattern there. So what does this look like? This looks like a horizontal line, right? The other derivative or the other approximation looks like a vertical line, and this one looks like a corner. So this is the objective and the intuition behind these convolutions and these approximations, to find these patterns of a corner, vertical or horizontal lines in the image. And why do we want to find those particular patterns at this stage? Because those generally tend to correspond to salient regions, right? When the pixel intensity is changing dramatically, as in this case from white to black, as in a line, then you have a salient image, or then you have like a different object segmentation. So this is what the key point detection step is doing, and is doing it in a very intuitive and fast way. So again, if you have a high number, once you put the filter in a certain region of the image, it means that like it's almost like blinking, like, oh yes, you're finding it there. If the number is really low, it means that you are not finding that activation in that particular area. So if you put those filters in this black background, you are not going to have really highly activated or high numbers in the convolution, but you're going to have those high numbers or those high feature maps in these lines. Okay, so this is what I told you. You blur them, you stack them, and then when you find the highest number of these feature maps, then you detect that there's a key point there. And you can impose different thresholds of what a high number of the convolution means, and that's going to detect whether you get more or less key points in your image. Is that kind of clear? I'll wait. I'll count to 10 in my head. So you guys, if you have any question here, we can talk about it.
Lots of thumbs up, so I think people understand.
Perfect. Perfect. It took me a long time to understand this. You can't imagine how much I had to read about this. Okay, so now we identified our key points. This comes apart in which we need to translate those key points into vectors or some numbers that we're going to feed our algorithms, right? So now we're going to talk about feature extraction. And I'm going to talk about a root sift, which again, we have multiple descriptors that you can use depending on your needs and depending on what computational power you have. But the root sift is also very efficient, it's also very fast, and is a nice, accurate way, or at least I like the way in which intuitively is characterizing some of these key points. Okay, so you're going to start with a Gaussian blurred image. We always do that again to like remove some impurities of the image and to avoid latching or focusing on things that are not really salient or important from them. And then for each of those green points that we identified, we're going to draw a 16 times 16 neighborhood around each of these key points. And we're going to overlay a grid with cells of size 4 times 4 pixels. Then we're going to estimate gradients in each of these cells, and we're going to concatenate them into a histogram. And we're going to take the square root of this histogram, normalized also by the distance to the key point, and we are going to end up with a feature vector that is of size 128, corresponding to 8 bins per histogram times 16 cells. I went super fast through this, but I'm going to go now slowly, crazy slow, to explain to you how it works. So again, you're going to take a key point, right? One of the green key points that we saw in the slide with them plotted. We're going to take a key point. Then we're going to take the 16 times 16 pixel neighborhood around that key point. We're going to divide it into cells that are of size 4 times 4 pixels. So 1, 2, 3, 4, 1, 2, 3, 4 here, each cell, right? And then let's focus on one cell. We're going to focus on this one. In this one, this is the pixel intensity of the pixels in these cells. As you see, the white ones have 255, the black ones have 0, okay? Now, we're going to estimate the gradient orientation and magnitude for each of these pixels in that cell. How are we going to do that? In a way, it's also like putting a filter in them. We're going to see how the pixel intensity is changing along the X and along the Y direction, okay? So in this case, we want to see how much is changing from this pixel here to this pixel and how much is changing from here to here, okay? So if I tell you how much is changing from 255 to 255 in this direction, it's going to be 0, right? There is no change in that direction. But if I tell you how much is changing from 255 to 0, then it's a maximum change that you can have, right? So we're going to do exactly the same thing and see how the pixel intensity is changing in those directions. And that's going to be represented by these vectors. So in this case, because here we like nothing is changing from here to here and from here to here, there is no vector representing change. It's null, it's 0, right? But here in the point that I show you, we didn't have any change in the x-axis, but we had a sharp, like the maximum amount of change in this direction, right? So that's the reason why for all of these cells, we are seeing a vector showing this drastic 90-degree change. Now, we're gonna summarize all of these vectors and all of these changes with a histogram, which is called a histogram of gradients. We're gonna, you have all of these potential angles in which the change can go, right? Not only like this or like this, but you have like multiple angles, 180 if you are using them unsigned. And we're gonna collapse them into bins. So the first one is gonna go from 0 to 20 degrees, right? And like the others are gonna go there until 180. And then we're gonna weight these changes in pixel, all of these vectors by the magnitude of that change. So in that case, it was the strongest change. Those vectors had the strongest change possible. So the height of the bin in that histogram is going to be really high. And apart from weighting them by this magnitude, we're also going to weight them by the distance to the key point. So these histograms are going to have a much higher weight than these histograms here, because these are closer to the key point. So are telling you more about what's happening in that neighborhood. So at the end, if we do this for all of these 16 cells around the key point, we're gonna have 16 histograms, right? We're gonna concatenate them, just flatten the full matrix, put them together. And at the end, this long vector is gonna be represented by 128 elements, which are the 8 bins that we had in each of our histograms times the 16 cells or the 16 histograms that we had. So remember your color descriptor with 4 numbers, with 6 numbers, the mean and standard deviation of the 3 channels. Here, instead of having these 6 numbers, we had 128 elements that are coming from this data manipulation, this dimension reduction of these pixels. So we are giving meaning to those pixels in this way, which is we are defining a feature as change in pixel intensity. But again, there are multiple ways of defining this.
Michelle?
Yes.
We have a question in the chat regarding kind of the direction of gradients.
Mm-hmm.
Do you calculate the change both in the x-axis and the y-axis and average them to get the diagonal ones, or do you choose the direction of the change?
No, you have to take both into account. So it's here. So the final gradient, it's going to be, well, the angle is going to be with this formula and the magnitude is going to be with this. And it's both taking the one into the x direction, in a y direction, and the angle is already representing change in both directions. That's important.
Perfect, thank you.
And just so you know, this looks like a lot of work, but if you compile OpenCV from source, it's literally one command that you, like one line of command that you have to run, and it automatically detects and gives you this. Okay, so now we have all of our feature vectors, right? So remember, we have our image. We calculated a bunch of green points. Each green point is going to be represented by these long vectors. What do we do with them, right? So we are going to define a visual vocabulary. And this is important because, once again, like unlike text, we don't have words, sentences, engrams, or something that has a meaning on their own. You know, it's not like house, and then you have the word house. Here in images, now we have a vector that probably is hard to even visualize right now, right? Because it's just like representing these changes in pixel intensity. For that, or in order to build this visual vocabulary, we're going to do the following thing. So here, suppose that you have these 3 images. Suppose that you estimated those green points there. I'm making them bigger just so you have a better idea of where they are, just for illustration purposes. And then remember that these key points have their own associated feature vector. We're going to map all of these vectors into our multidimensional space, and then we're going to cluster them. In this case, I'm using a mini batch k-means because with that many vectors, it's a way faster and more efficient than a normal k-means, but you can basically use any clustering algorithm. This is just one of the most basic ones. And even though it's in mini batches, which tends to decrease the efficiency tad, it still works really well. But you can go as ambitious as you want. So you cluster all of your feature vectors, and then you estimate the centroid in each of these vectors, in each of these clusters. And this centroid, which is also a vector of size 128, which is basically the mean of all the feature vectors belonging to that cluster, is going to be your centroid. And this centroid is going to be your visual word. That's going to be representing your visual word. So intuitively, this is a cluster of mini patches. Formally, the vector is representing the centroid of the cluster. Okay, so these are examples of the visual words that you can construct. So in this case, you can see there are mini patches of like crowds or groups of people. This one is a visual word with mini patches of water bodies, and a bit of like a silhouettes or shadowy contrast. And this one is a visual word with mini patches like of a fence or a wired border. These are all taken from pictures of the caravan of migrants from Central America. Okay, so again, this is how a visual word would look like, or that's the way in which we are interpreting it. But this representation is actually really helpful because now, instead of having these numbers or these vectors that probably don't make a lot of sense if you look at them, although they are making sense for the computer, you as a researcher have a better idea of how they look like or what they are representing. And that's going to be helpful when you're trying to explore what kind of words are determining your classification, or even for validation purposes, for qualitative analysis of your images, and for quality purposes, basically. Okay, so once we have our visual words, we can build our image visual word matrix. And what's this? So as I mentioned before, the image visual word matrix tries to emulate the document term matrix in text. And I know all of you are experts in that, but still I'm going to give you a brief refresher. So a document term matrix looks like this, right? You have your texts in rows, and in columns, you have the words that appear in each of these rows. So in this case, president, elections, migrants, troops, etc. And then we're going to count the number of times that each word in each column appears in each row. So in this case, president appears once here, elections appears once here, but for example, here, president appears twice, right? And the idea is that based on this matrix, we can find a lot of patterns. Now, this is what we have in text. With words, we're going to try to do the same thing with the visual words that we identified. So we're going to have our images in our rows, we're going to have the visual words in columns, and then we're going to count the number of times that each of these visual words is appearing in these images, okay? Now, this is a little bit less intuitive than counting president and president here once and twice, right? How are we going to do it? So remember that we create our code book. And what's our code book? Our code book is basically the centroid of the clusters that we identified of the feature vectors, right? So we have our image, we identify some key points. We're going to take, for example, this little guy. We're going to map it into our multidimensional space. And then we're going to take the distance between each centroid and the feature vector of the key point, okay? So the idea here is basically to see which visual word is the closest to that particular key point. So in this case, this visual word is the closest to word number 2, right? So we're going to say that that key point is associated with word number 2, and we're going to count it. We're going to like start our count. Oh, okay, this image has one word 2. If this one also is a word 2, then we're going to add it, etc., etc. Okay, that's the way in which we're going to count our visual words in our images. Okay, So some considerations here. Remember, the clusters are visual words. The centers of those clusters are the actual definition of the visual word. And the way in which we are defining how close a given key point is to a visual word is by estimating the Euclidean distance. So also a very simple formula there. Something to remember is that because of this method, every key point, or the way in which I implement it and the way in which I'm going to give you a code is that every key point is assigned to one word, because you basically estimate the distance and you're like, okay, pick the minimum one. So if one keyword is still very far from everything and is super dissimilar, it's still gonna be assigned to the one which is the closest. So there are ways, of course, of dealing with this. You can put a threshold, or you can say, okay, no, I want these just this far from the key point. But just so you know, the code that I'm going to give you is going to assign every key point to a visual word. Okay. So now in practice, what are we going to do with this image visual word matrix? But before I dive into that, any questions?
No, nothing yet, Michelle.
Okay, perfect. So I don't know if you guys are fans of The Amazing Race. I am. And the pandemic made me go through, I don't know how many seasons. I literally can't recall. So I got a bit more obsessed than I was even before. So here's a speed bump for you. The Bank of Visual Words approach, it's just a summary of what we just saw, helps you to reduce the dimensionality of pictures, right? Like that's the goal number one, to give meaning to all of those pixels in a much more condensed way. We extracted features and linked them to tokens or references that we created and that we named visual words. And we built a document term matrix style input, which is an image visual word matrix, or we're calling it that way. But then what? What are we gonna do? Now you need to choose your detour, okay? You can do sentiment analysis. You can do binary classification with that image visual word matrix. You can do clustering analysis, or you can even do topic modeling, right? Like there are multiple ways. Like once you have that matrix, you can do a lot of things for classification purposes. I generally choose and recommend to do something more exploratory and unsupervised. And in this particular case, what I generally have done with my research is to use topic modeling. And in particular, I use it with a structural topic model developed by Roberts et al. Again, I'm pretty sure you guys know about this, but this is a tool for topic modeling of text with document level covariate information. And that one for me is one of the best things. And that's why I really love using the Bank of Visual Words in this setup, because it not only allows you to reach classification in terms of what topics are in your images, but it also allows you to test the effect that these document level covariates have on that classification. And that's something that I find really neat and important as a social scientist. The topic model is just this mixture model where you have probability that the words belong to each of the topics or groups of interest. And it doesn't give you a single classification outcome. It doesn't tell you, oh, this image is about a crowd, or, oh, this image is about a kid. It gives you a proportion of all potential topics for each document. It's going to tell you, oh, this image is not only about a crowd in the field. It's going to tell you, look, there are some topics that you can find in this image, and you have a proportion of those topics. So you have mostly sky, but you also have a crowd, but you have also a bit of pavement and even some flags. So if those are the topics that your STM could identify, then you're going to have proportions for each image of interest, which differs a lot from some of the clustering techniques that you see in computer vision that just tells you, oh, this is a picture of a crowd. And again, this is nothing bad. It's just you have different research interests, you have different questions, and sometimes it's harder to find questions like this in other fields of like what things can you find in a more mixture style way. Okay, so I'm going to show you an illustrating example using the pictures from the migrant caravan from Central America to the US. These caravans were a group of migrants fleeing violence in their countries and seeking refuge in the US. And they created a lot of political tension when they started their pilgrimage. There was a lot of polarized coverage of the phenomenon, and as you can imagine, based on who was covering this event, was the flavor of the coverage, right? So there was a lot of emphasis on the magnitude of the caravan by certain outlets, basically saying that it was a threatening movement and that it was like an invasion. So this image, for example, was used by certain media outlets with statements like this: massive migrant caravan on the way, looks more like an invasion than anything, whereas other outlets were using images more focused on who was coming, right? And talking about how, see them as they are, desperate, living behind whatever they had, just like looking for a better life, right? So this idea of like, we are seeing this phenomenon, we are interpreting it in different ways. Let's focus on what we are trying to picture with, like what we're trying to say, but illustrated with pictures. So we think it's an invasion. Here is your invasion. We think that these people are like really, really concerned and worried, and are just like looking for a better life. Close up on the people, close up on the kids, close up on the women being really tired and exhausted after the pilgrimage. So as you can see, there were different coverages of the same phenomenon. Okay. So I saw these images and I was like, okay, I want to identify and quantify this visual framing of the magnitude of the caravan. How are media outlets framing the size of this phenomenon? And for that, I used a structural topic model to identify underlying topics in this pool of images that I am equating to frames in the images. So if you are using a frame crowd in a much higher level than other outlet, then my assumption is that you are trying to frame or like use images to frame the movement in a much more invasive or threatening way. Okay. So I generated a visual codebook from 6,000 pictures from Getty. So remember this stage where we try to define our visual codebook to generate these tokens. I got all of these pictures from Getty with the idea that it's an unbiased source, right? Because they have multiple photographers, they have multiple journalists and multiple agencies in the field. So I'm always thinking that my assumption is that if you have that variety of people, then you are more likely to have a richer picture of what was really happening. Like every single one of them is going to have their biases, but at least here we have a collection of biases that allows you to have a fuller view of these events. So my assumption then is that if you have this fuller image, that's really the best that you can get at what really happened. So that should be your benchmark to construct a visual codebook, right? Like, oh, this is everything that you can find. Here is my codebook, let me build it. And then this is my sample of interest. Let me see how this sample of interest is comparing, or is how is it differing from this full set of the benchmark, or like the true benchmark, okay? I had 500 words in my vocabulary, or visual words that I set, and I used 2 prevalence covariates, document level covariates for the STM, the agency, and the date. And I had 6 topics: border fence, small group, water sky, camps and darkness, and crowd. And I'm going to focus on crowd for now, just to give you an example of how it worked. So you can ask STM to give you the most frequent and exclusive words for each topic. And I created some functions in R that I'm going to share with you to adapt it to these images. So instead of having the most frequent and exclusive words, you can have the most frequent and exclusive visual words, right? So for the topic crowd, these were the most frequent and exclusive visual words. And as you can see, all of these clusters of mini patches with crowds. For border fence, also these mini clusters with pieces of the wired fence and the border. For water sky, these mini patches of like basically light colors with splashes of either waves or clouds. And when you ask STM to give you most representative images, so basically a representative image of a topic is that one that has a high proportion of this particular topic that you're interested. So for crowd, you can see that the most representative images are definitely containing these big crowds. For border fence, the same thing, and for water sky, the same thing. Okay. So, okay, let me wrap up and then I take questions. So the wrap up for the bag of visual words is that it's very clean and it has like a very traceable way of defining features and extracting them. As you can see, every single part of the process, it's like clearly identified, and it doesn't vary if you add more images, for example, for the feature extraction. No, nothing. Here is your formula for estimating the gradient magnitude and orientation. This is your formula for combining them. No matter how many images you have to have your visual codebook, it's always going to be the same feature extraction process. And it's really nice because it also leads to this visual representation of these features, which helps to, in this case, for example, analyze whether this STM is working or whether it's giving you sensible results, and also to do some validation exercises or to have a deeper understanding of how these topics are created, right? It also allows you to use models that do not require training or label data. So again, in this case, I just fed my image visual word matrix into my STM, and I got some results in a very agnostic way. So it's then therefore very helpful for exploratory analysis, right? If you want to have a first pass of your data because you have 20,000 images and you are actually not very sure of what's in there, this is a great way of like having an idea of how these images are behaving. If you want something more specific, if you are particularly interested in identifying a bird in the images, then this is not going to be the greatest method for that. But if you really want to have an idea of how the topics or how the themes in your images are getting distributed, this is a great thing. So no color though. This is all based on grayscale images because it's pixel intensity change in grayscale images, and it's not super accurate if there are very particular concepts that you want to measure. As I said, if you have a very clear idea of what you want to identify, then this is not going to be the best method, but then you will have CNNs to the rescue. Okay, so questions about the bag of visual words?
Yes, we have quite a few questions.
Okay.
I think if you don't mind, Michelle, it might be helpful for everyone to go back to the slide where you have where you listed 4 applications for visual words. There's one question that's asking if you could elaborate more on those 4 practical applications, and you kind of explained topic modeling, but specifically one question regarding sentiment analysis of, is it finding emotions through pictures or kind of the vibe of the photo?
That's entirely dependent on what the researcher wants to do. Like you can think about using a trained algorithm here, similar to what you would do in text, and like define what visual words, for example, build a dictionary and define what visual words are happier or are either giving you a more positive vibe of the image, or what visual words are actually making people happier. Like that's going to depend on the question of the researcher and the way in which they are going to define that dictionary, for example, to then conduct some sentiment analysis, or they are going to use that image visual word matrix and have some pre-trained images based in either, oh, this is a happy image, or, oh, this is making a person happy. I generally, again, you can actively and for sure you can use them for example, oh, what emotion is evoking, but I'm generally cautious or more hesitant to recommend it as such, because I think that's a very hard and subjective concept, right? If like for example, for me, an image of a puppy always makes me happy, because I love dogs. But my husband was bitten by a dog when he was young, so he doesn't like dogs, and pictures of image have zero effect or negative effect on him, right? So if you load those pre-trained images or that pre-trained classification into your algorithm, the computer is going to be like, wait, this is exactly the same picture, and what am I looking at? Like, how am I going to classify this if I'm getting two contrasting messages there? So you can still do that, right? Like, because maybe your classification is going to be, oh, 80% of people think this is a happy picture, so I'm going to consider it that it's evoking positive reactions in people. But I'm just saying that because it's such a subjective thing, sometimes I'm like, I don't know if I actually don't know how to train the computer to really see that, because the concept is quite abstract, if that makes sense. But it's way more common to be like, oh, this is a happy image in general, or this is a positive image, right? In general. And that's how you could use them. It's going to depend on your research. The point here was that image visual word matrix can be the input for it, or you can use it to train an algorithm for that. So that one was one question. The other one, Alex, was explain topic modeling more?
No, can you provide an example, like just a short example of what binary classification would be your cluster analysis?
Oh, yeah, sure. Yeah, sure. Okay, perfect. So for binary classification, similar like with sentiment analysis, maybe you're interested in detecting a crowd. Then we go back to this idea of like, oh, I just want to see if this picture has a big crowd or not. Then you have your pre-trained set of images and be like, okay, these images have a crowd. This is the visual word matrix associated with them. And then you train an algorithm to learn the patterns that define that crowd. It could be a support vector machine. It could even be a logistic regression if it can handle it. And then you use your image visual word matrix to have on-label images to see if there's a crowd or not in those images. For clustering analysis, it would be very similar to topic modeling. For example, if you just put all of your images, and then instead of having like a topic or like a distribution per image, it's just going to tell you, oh, this one belongs to cluster A, this one belongs to cluster B, this one belongs to cluster C. So similar to what we saw with the color histograms and the color statistics, maybe you have political propaganda images, you have your image visual word matrix, you run a k-means on that visual word matrix, and it tells you, look, these are the cluster A environmental propaganda. Well, it's not going to tell you this is environmental propaganda. It's just going to tell you these belong to cluster A, and then you can look at them qualitative identification and be like, oh, yes, most of them are environmental. These are about war, cluster B, cluster C. These are about radical right propaganda, right? So then it is just giving you a very factual classification, a single classification of how each of the images are distributing along different clusters.
Building off kind of clustering, is there a need to validate your clusters, i.e. intra or inter-cluster validation?
Yes, so that's a great point. So actually, I'm going to talk about validation, not only for clustering analysis overall, but for example, for the visual, when we're doing the clustering to create the visual words, I'm generally, I use script plots or like elbow plots to see where at what point the within cluster sum of square errors ends up being not meaningful. There are no drastic changes. So the code, for example, that I'm going to share also can perform those tests and can give you the plot, so you can see, oh, this is an optimal or a decent amount of cluster. It's not a super strict test, but it tells you where you can draw a line and be more systematic about like, oh, I think this is the optimal number of words that I need, because that's something that you need to define, right? And you can do exactly the same thing with a normal clustering algorithm. At the end, I think the most important thing is always going to be, for validation, do it more in a qualitative way. That's the reason why I always say the computer can help you, but the computer is not going to replace you, right? Because you always need to go back, sample some images in cluster 2 and see, okay, one of my teachers always says that this is like tea leaf reading, and it's true, but there's not a lot that we can do. And it's like, most of these things look like this cluster belongs to this particular label. Most of these things look like this. And then you give it to coders or to a group of students and you ask them, what do you see there? So it's not only you and your subjective and kind of biased and motivated way of interpreting the results, right? I generally, Alex actually helped me recently, and I gave her some topics, I gave her some results from the STM, and I was like, what do you see? I'm not going to show you what I think, just give me what you see. How would you label this topic? What kind of words you see there, etc. And that's another way, in a more qualitative way of determining if they make sense. There's also a nice package by Lu Wei Ying, Jacob Montgomery, and Brandon Stewart. It was recently published in PA, and that uses crowdsourcing resources. So you basically use mTurkers to tell you what they see in the topics, whether the clusters make sense, whether the words that are there make sense. They give you labels. They have like multiple tasks to actually confirm or have more evidence that how you're labeling them and how you're identifying actually is correct.
Great. So we have a few questions regarding the actual kind of image process. So I know you said that you do have to make them black and white. Is there any other pre-processing of images that you have to do in order to use the bag of visual words? And what does that process look like?
That's an excellent question. Yes, you need to transform it. That's one step. Grayscale, make them grayscale. The only two things that I do with my images for this process is just I make them the same size, and I transform them into grayscale. That's it. But you can do more things. You can try to normalize them. You can account for coloring, for example, or try to make them use the same or like a similar resolution, etc. I just resize them and make them grayscale. Sometimes if you're using, for example, with Getty is really good because they are almost all the same resolution and size, etc. So there's not a lot of things to be concerned about. But if, for example, you're using Facebook and some of them have memes and some of them have thumbnails and some of them have really small pictures, when you try to make them all the same size, some of them get super pixelated. And I ran some tests and it generally does very well, even with not so great or like not high resolution images. But if it's super pixelated or if the thumbnail definitely got distorted, then you're just going to get a topic or a cluster of bad quality images, like nothing about the content, but just about how bad they look. But I guess there's not a lot to do with that. But yes, the pre-processing, you can go very basic with just resizing.
So debating where to go. So one question that came up is similar to bag of words. Does the visual bag of words also work better on institutionalized input data? For example, images coming from CCTV or dash cams? I would say that, for example, in this case, the symbol that I could find is Getty indeed, where they are more curated or more like they are of higher quality and it works really, really well. That doesn't mean that with Facebook, I have no real, I'm trying to think of a parameter that would tell me if it works better or not. And it's just more like experience and like intuition or like anecdotal evidence that probably, yeah, it's better or smoother to work with those images and with like blurry ones or like less standardized ones in a way. But I actually don't have a very, like, and this is just like my personal sense. I don't have a number or a statistic to tell you of whether it's working better or not. But yes, for sure, if you have better images, then I think it will work better. In your specific migrant example case, can you elaborate how you selected the initial samples from Getty? And also, how were they classified? Kind of how did you identify ones that were related to the migrant caravan?
Yes, that's a great point. So I literally just put in Getty migrant caravan of Central America, and then I chose a time period, though I didn't choose the entire sample, just like a time period that I was interested in, especially with respect to the things that were happening in the US in terms of the timeline. And I restricted them to be from sources publishing in the US, because again, I was interested in how the American media was portraying them. Those are the filters that I would put, but any picture that had a migrant caravan as a tag was included in the sample. And I checked, and all of them belong to the migrant caravan. It was nothing unrelated to that. Those were that was the criteria. That's how I got the almost 6,000 images. For my sample of interest that was coming from news outlets, I used the news API with the parameters, the time parameters set exactly to those from Getty. And the news API just gave me all the articles mentioning the migrant caravan and all the related images to them.
Perfect. And someone did ask if we would be able to go through an example of how to use image virtual world matrix into a sentiment analysis. I don't think you have the code for that, but do you have any recommendations on places to look for that? Or
yes, we're not going to cover that. But yeah, I can not at the top of my head right now, but I will definitely look into that. I will also tell you that with CNNs, for example, which are going to cover in a sec, we're definitely, there are definitely some exercises made by researchers. Actually, the example that we have is, for example, in detecting trustworthiness, happiness, sadness, angry faces in pictures of faces. So there are other attempts using CNNs to detect this like sentiment of the pictures more than with the bag of visual words. So that might be helpful. But if you want to use a bag of visual words, I am happy to look for resources and send them.
perfect. I think that's all the questions. Just one, I think, clarification. The grayscaling and resizing is done by this OpenCV programs. Otherwise, you don't have to do it prior to loading images.
No. OpenCV already, there's OpenCV or even a package called IMUtils that it's pretty good, and you just, it's basically like a pre-canned feature. A lot of things in computer vision, especially the basic ones, involve the grayscaling. So it's a very, very standard function, and similar with resizing. And even then, like sometimes they pad and they use all of these interpolation. For example, if it's a small image and you still want to make it bigger because of the size of the others, it automatically does everything without you having to manually alter them before feeding them into the algorithm or everything. All good?
Yes.
Perfect. These are great questions. Thank you, everyone, for engaging so much with the material. I hope this is helpful. Okay. So let's talk now about convolutional neural networks. And probably you have heard a lot about them if you've read a bit about computer vision, and it's because they are probably the most common and popular ones. And now they used to be hard to actually run, and you needed a lot of computational resources like a GPU in your computer to actually train these models. But there's something, well, first of all, it's cheaper than ever to actually get access to some of these resources. Like Google Colab, for example, offers you these virtual machines with one GPU, and for like not a lot of money, you can get even more power and more GPUs there in case you really want to go crazy and train your CNN from scratch. But there's also another concept called transfer learning that we're going to cover that has really made the use of convolutional neural networks way more accessible to a wide variety of researchers, not only computer scientists with crazy machines in their offices. Okay, and well, the idea is that all of these techniques, the neural nets and the convolutional neural nets, they are meant to emulate how human brains transform the sensual stimuli into conceptual understanding. So they have this really, really ambitious goal that I told you about, that they really want to replicate the way in which humans see and process visual information. They want to do the same thing and import that system into the computer so the computer can replicate it. In this case, remember that I told you that generally the way in which we were understanding the relationship between computers and humans is that we will give them a set of instructions and they will follow them. In this case with CNNs, because there is this acknowledgement that we just can't give infinite instructions to identify the things that we're interested in, we are allowing the computers to set their own set of rules to classify information. So basically, we are just going to give them some specific parts and they are going to learn the patterns and determine what's important in those patterns to create this set of rules that leads to a particular outcome. Okay, so the idea or like the name of neural network comes from neurons, indeed, the neurons that we have in our brains. And all of these neurons takes inputs, right? That take this visual stimuli, for example. The different neurons are gonna digest the information. They're gonna get activated if something is particularly important. This is based on the strength of the stimuli and the saliency of that particular feature. They're gonna sum and transform it and digest it to finally get an output. To say, oh, this wall is yellow, or oh, this animal is a cat. So to finally get an output that the brain can really use or that the human can find helpful, a lot of this processing is going behind the scene. Okay. The cool thing about this is that we have multiple neurons, right? Like even though one neuron is taking care of a tiny task, when they connect and they talk to each other, then you get the full system that allows you to process very complex information. So just as in the brain, these convolutional neural networks really want to have these neurons organized into layers. And again, every layer composed of different neurons is going to break down the signals that they get into small pieces, allowing each of them to focus on a unique piece of information. So the cool thing is that each neuron tackles one easy task, and then they send the result to the next layer. So the next layer has a more ambitious or more complicated task. Okay. So the way in which it works with neural nets and images is that the first layers are going to identify really basic features like simple lines or simple corners. The intermediate layers are going to transform, or like once they have some information about whether there are some lines and corners, they are going to start creating more complicated patterns like combined shapes or some object detection. And the last layer is going to make, it's going to even put more complicated more information together into more complicated patterns using colors, textures, the full object, etc. So it's going to be like a step-by-step pyramid here. So that sounds very complex and very not super clear, right? I recently been reading a very sophisticated text, and I've been reading it a lot, almost every day, that is called Neural Networks for Babies. As I told you, I have a 6-month-old baby, and my advisor gave this book to me. And it's actually a pretty good book for understanding how neural networks are working. So no, I am not joking. I'm really reading it to him almost every day. And I am borrowing some of the content from this book so you can get the intuition of what's happening with these neural nets. So I am skipping the part when they explain that the neuron is like a ball that receives an input. And once you put that input into that ball, it's going to give you something. It's going to give you an output. So in this case, if you have a question of, is there a red animal in these pictures? There are going to be multiple neurons trying to answer that question, but not the full question, but small parts of that question. So there's going to be a neuron, for example, that is going to analyze different parts of the image and determine whether there's some red in that particular section or mini piece of the image. So if you have 4 pieces, like in a puzzle, it's going to say, yes, in 3 of them, there's red and there's 1 blue, right? And then the neuron is going to tell you, I think there's something red. Like it seems like 3 out of 4 parts of this image have some red. So I'm going to say yes to the red. And it's going to send that message. That's going to be the output. Similarly, if the question is, does this animal have 8 arms? Then the neuron is going to observe the different parts. It's going to count the number of arms, for example, and it's going to send that message. So it counted 8 and it detected that there's a lot of red. So that output is going to be sent to other neurons. These neurons are going to talk to each other. They are going to connect in this network. And at the end, based on all of these signals that the individual neuron sent, then it's going to tell you, I think there's an animal there, right? Like you told me that a red animal has legs and it's red. So if I find those things, then I think I'm going to tell you that there's a red animal here. So that was a very easy way of explaining to you. I'm sorry if it was too basic, but I thought it was very, very intuitive when I first saw it. But yes?
Just off of that, so what if an arm lies between 2 kind of grid points in that picture?
Oh, well, that's the thing. So here it's like very, very cartoonish because it's only four pictures. But generally the filters that you use are actually quite small. So it really goes through really, like it explores the image like with a lot of detail. You can also manipulate that. Let's say if you're looking for, I don't know, like the people in a very large crowd, some of those filters then might need to be smaller, but maybe if you're looking for features in a face, then the filter will have to be bigger. I'm going to talk about filters in a second. So you can also define the size of those filters depending on your question. For most of these things, it's going to be basically trial and error. Like maybe you can start with a standard filter of like size 32 and 32 pixels. And then maybe later on, you're like, no, probably it's not quite finding what I want. I'll go smaller or I'll go bigger. It will depend on your question. So then that decreases the chances that the leg is just like right in the middle. Like maybe if you really want to check the legs, you need a bigger filter or in that case. Does that answer the question?
Yes.
Perfect. Okay. So that was the neural nets for babies. The adult talk is here. And it's that CNNs is a supervised learning algorithm to classify images. CNNs gradually learn what visual features of the image are more important in a classification task. So that was very cartoonish because the computer is asking, how many legs? And in reality, the computer has no idea what a leg is, right? Like they just see like a pattern, a particular set of pixel intensity changes that looks like this. And they're like, okay, I'm finding this in these images. I'm going to consider that a feature. And I'm going to say this particular feature that I have no idea how it's called, it's present in that image, right? So they learn those visual features. You are not inputting, you are not like defining those visual features. They are going to learn them based on the images that you're going to feed them. And they are going to create these feature maps, basically. They are going to define their own filters, and then they are going to do something similar to what we did at the beginning. They're going to slide through the image and be like, oh, is this particular feature here? Yes, no, how strong? And it's going to create a feature map of all of these filters that we are going to have, okay? The CNNs are organized into multiple layers. Each layer contains multiple representations of the original image through these feature maps based on this definition of features that could be edges, blobs, color combinations, textures, everything. In CNNs, everything can happen. And in that sense, you don't have a lot of idea what's happening there with respect to those features. Like, again, all of these statistics, and I can show you, but it's not that you can see from the beginning what type of features it's going to look like and what kind of features it's learning. There are methods for that at the end, but Alex and I have been talking about this. People talk way less about them because they are generally not interested in what drove the classification, but just in the actual prediction. So we can talk more about that at the end, but just so you know, at the beginning, you don't have a lot of flexibility in choosing those features because the idea is that the computer is going to learn them from the patterns that you're giving them as input, okay? How are they going to learn those patterns? Well, it's going to be also very similar to what humans do, which is by trial and error. So you're going to give them a training set of images and be like, look, this is how a dog looks like. Now go and look for a dog in the images, right? So based on this information of how a dog looks like, it's going to create trial and error and estimate this prediction error multiple times until it minimizes the number of mistakes that it makes. And it tells you, okay, based on this minimal error, I think these features are defining what a dog is. And I'm going to use that information to predict whether there is a dog in this other set of pictures that you are giving me. Okay. Generally, that's what they tell you as well with CNNs, that this training process is trying to emulate how humans work. But there's a strong school in computer vision that tells you, yes, it's trying to emulate it, but it's never going to be the same. Like a kid needs very few examples to understand how a cat looks like. And after seeing a cat 10 times, he has pretty clear what a cat looks like. And even if you cover the cat, if you hide part of it, he will still understand what a cat is. And in contrast, the computer will require millions of images to really identify it in a good way. So that's what I'm saying. If you ever want to train your CNN from scratch, it's a very, very intense task because you need a lot of images to make it work, right? The training process is generally really burdensome. So that's the reason why as social scientists in general, we will be more focused on use pre-trained CNNs and adapt them to our needs. And again, we're going to talk about that. Okay, so the network structure. We're going to talk about the goal, which again is learn the features associated with outcomes, right? This, we can also translate it as obtaining coefficients, which are going to be called the weights in feature maps. A weight, and that's what I always talk about in my presentations. So if you've been in one before, I'm sorry to repeat this, but also part of the reason why sometimes it's so burdensome to learn these things as a social scientist is not because we're not good enough at stats or math or programming to understand these things. It's just because they have a very different language. So I think at the beginning, when I started reading computer science journals, there was always the word weight over and over again. And I couldn't stop thinking about weighting. I also come from a background of survey methodology. So it was like, what are these weights and why are we weighting these things? And in reality, this is just like a coefficient, like a weight in an OLS regression for them. It's a coefficient. So just so you know, what we are trying is here to understand what important features are more prominent, or in this case, have a higher coefficient in these feature maps in determining the actual classification. Okay, so not a black box. Everything in this process, it's just at the core, it's this optimization of error. So to make the error, the prediction error, as small as possible. And everything that is happening in the CNN is actually mostly concerned about reducing the amount of data. And why? Because this goes back to something that we said at the beginning. Pixels are a lot of information. They make images really, really big, but they actually sometimes don't give as much information, or they don't give the relevant information to actually conduct classification, right? Like if we eliminate a lot of the background of images that are not telling you something, is probably going to be much better in terms of computational resources, and actually better not to confuse the computer on how to attach a label to a particular image. So a lot of what's going to happen is going to be trying to reduce all of these pixels that we see into these feature maps, and then estimate these weights through the hidden layer of what's important to actually give you a classification of interest. Okay, so let's start. This is how we're going to represent our images. This is, again, we have our matrix with pixel intensity changes, just in a grayscale image. But CNNs work with color images. You will just have your three matrices corresponding to each matrix per channel. So you have your input matrix, and then you're going to have different filters in each layer. And again, this is an example of a filter, a very tiny filter of size 3x3. And can anyone tell me what this filter looks like in terms of a feature? Or you can tell Alex, and Alex can tell me.
Okay, so Dominic says a diagonal line.
Exactly. So basically, when we are putting our filter here of a diagonal line, we are trying to look for that diagonal line along the input matrix. So we are gonna convolute or convolve. I actually don't know we're gonna use a convolution process here in each of the sections of the image. That it's like just these, like 1 times 1, 0 times 1, 0 times 0. And we're going to sum all of these numbers. And this chunk of this big input matrix is now represented by this 2.2, which means here, it kind of looked like there was like a diagonal line. I mean, kind of, right? But at least way more than in the rest of the pictures in the image. And you can already see how the matrix is starting to get smaller by identifying these feature maps and creating something more condensed or similar, okay? So the idea is that you're going to have a lot of these filters. You're going to have diagonal lines, you're going to have vertical, horizontal lines, at least in the first layer. Those initial filters are going to be randomly initialized by the CNN. And then later on, these filters are going to be created based on the patterns. In each round, it's going to learn something about the patterns, and then it's going to test those particular filters that it's creating throughout the process. But at the beginning, they are randomly initialized and they look pretty much like this, basic features, okay? Then you're gonna have a layer that with activation functions. And this is basically to use those feature maps as input and then create non-linearities. And this is important. Like intuitively, it's just gonna tell you what things are important or not. Like in this case, for example, ReLU is the most commonly used activation function. And it's like, if you have very low numbers with respect to in the feature map, meaning there are not a lot of like things shining there with respect to a feature, then just ignore it, put a 0. Otherwise, put the actual value. So in this way, we're also focusing on the things that are really, really driving the actual classification or the filters that we are definitely finding in the images. Okay, so in this case, I have an example with 10, right? And it's just applying that transformation to each one of these formulas. We're applying that to each of the cells in the feature map. And then we're gonna go through a pooling stage. And the pooling stage is just like simply a way of reducing the dimensionality even more. In this case, it's like, look, maybe these areas look very similar in the picture, so we might just at the end average them or have like some kind of thing condensing them more. So in this case, for example, we can use max pooling, which means we just take the highest number from that area. In this case, it's 0.537. Now for this particular cell, we're going to take the maximum again, 0.761, etc., etc. And we are reducing our matrix to make the computation easier, okay? A note here, recently in computer vision, the trend is actually not to do the pooling stage. Some people advocate for them because, again, when you're dealing with a lot of images, it can get like really, really burdensome for the computer. But of course, the trade-off is that then you're losing important or potentially relevant information by decreasing the dimensionality in this way. So some people still prefer to use some of these layers, like more feature map creation, that are also reducing the dimensionality, but in a more meaningful way, like by using more and more filters. So using more layers, okay? And the last stage, once we have all of these feature maps already really reduced and condensed, is to actually learn the patterns and come up with a classification. And the way in which this happens is by offering our CNN a lot of training data. and the process is actually called backpropagation. If you're interested in the math of backpropagation, is basically a lot of derivatives using the chain rule. I have them here, but the intuition is this one. And actually, this should be very familiar to all of you guys if you use an OLS. In this case, this is like a representation, a visual representation of the loss function, which is dependent on 2 weights. So this is in reality like something like the sum of square errors in our, or the mean square error in our OLS regression, and coefficient A and coefficient B, right? So we have this distribution of errors based on those coefficients, and we are trying to find that combination of coefficients that minimizes our error, or in this case, that minimizes the loss function, okay? So by finding the minimum point, we are finding the minimum prediction error, which is what we want, right? A model that can minimize the errors that we make regarding the predictions. And Alex shared with me a fantastic resource about how to explain this more, or how do we get to the minimum of this loss function. And it's that if you like imagine that you're in a field in a super dark place and you really want to find the lowest point in the valley, then you probably start crawling and like touching the field a tiny bit. And once you reach to a point where it's going down, 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 you keep doing it and you keep crawling kind of like slow and steady until you get to a point when suddenly you start going up. So once you reach that point, you are kind of confident that at least you reach some minimum point of that field in the dark. So that's what our algorithm is going to do. It's going to basically have this multi-dimensional space that we can't even picture in our minds, because we don't have 2 weights, but we have tons of weights there. Tons is an exaggeration, just like thousands of weights there. And the algorithm is going to explore it until it finds a minimum point, okay? So this is called the gradient descent, and it's going to allow to update all of the weights in the neural network until we find an optimal combination that minimizes the error. The core of this statistically is just estimating derivatives through the chain rule. And here, for example, it's all going to based in, again, trial and error. You want to estimate, for example, in this case, what's the error when your target prediction is 5. And in this case, for example, the arrows in this network are going to be the weights or the coefficients multiplying the inputs. So in this case, we have 3 times 2, right? Here is going to have 3 times 2 and 2 times 1, so 8. And here is going to have 3 times 0, 2 times 0, right? And then 0 times 2, 8 times 2, 16. And if our target was 5, you can see that your error is 11, right? So that's going to be one pass in our neural net, and it's going to be like, 11. Let me see if I change this to 1, how does it change? Do I get closer to my target label or not, or my target output or not? And that's the process in which we're going to do it. And how do we get this target or desired outcomes? Using our training data. If you give the CNN a set of images with specified labels, then you're telling them, this is a target. You should aim to correctly classify these training images like this, modify the weights accordingly so we get a perfect classification, okay? So I'm going to show you an example with handwritten recognition that I actually will show you, not this exact application, but something very similar. This is a textbook example of how to run a very basic CNN. So this is, and I like this application for the following reason. So detecting handwritten numbers in computer vision, it seems to be like a foolproof example for everyone, right? So Francisco Cantu, one of my favorite scholars in the whole world, who works at the University of Houston, approached me and told me, hey, I have all of these tallies from the Mexican election in 2015. they have handwritten numbers. Let's write a paper about how CNNs work using this example and trying to classify the handwritten numbers in those tallies. Eventually, I want to create this, or I want to really analyze it to create an app or like a system that speeds up the reporting of elections in Mexico, because now everything is by phone and by hand. So it's a mess, and it's like prone to so many human errors, etc. So if we design a CNN that can read these handwritten numbers, then we can talk to the electoral institution there and be like, let's do this. Let's tell your poll workers to take pictures of the tallies, and we will classify them in like 3 seconds, right? And then you don't have to wait for the phone number or anything. It's going to be so easy, safe, secure, and efficient. So I was like, this is a great idea, especially because CNNs are really, really good at reading handwritten numbers. So I was like, this is fantastic. It's going to take me like literally 5 days to set it up. I don't think it's going to be longer than that. Well, long story short, 2 years later, I was still struggling with this CNN and the accuracy I was getting. And this is because in computer science, all the models designed to detect handwritten numbers use this training set called MNIST data, which is this beautiful set of numbers that are really clean and nice with a white background, no stains. They are perfectly curated. And all of the models have been tuned and designed based on that data set. And again, that's something in the field that's important for them, because they want to increase the accuracy. And the only way in which it can be comparable between models is to use the exact same data set. That benchmark was the only thing used. So then when I plugged my tallies, which are less than perfect, then the model did not do that well. So that's the reason why sometimes things that we find they are super bulletproof and, oh yeah, this is a great model, we still need to remember that we have to do a lot of things to clean our data, to make it suitable for what we want as researchers, okay? So in this case, this is a tally that we were interested in digesting. These were the numbers. And as you can see, this one is actually a pretty clean one. And still the model really struggled to classify the numbers because these bounding boxes were confusing the model. In the training data, they didn't see any of these bounding boxes. So they were like, I don't know what's happening. And sometimes there was like pencil marks or like a spill of coffee or like some issues with the scan, and it looked like more light here. So it was a total mess. We had to do a lot of manipulation of the actual, that one had a lot of image pre-processing involved, for example, to make them a bit more suitable. And still we had to train our own CNN because the out of the box wasn't working. Okay, so this MNIST data set that I was telling you about had 17,000 samples of numbers. The models that you generally use were trained on 60,000 of them and then tested on 10,000. If you only use MNIST data with them, you can reach accuracy levels of 19.3, sometimes even 99. So really, really high accuracy. Again, textbook example. But with our real data, once we tuned, cleaned, created our own model, the highest we got to was 96.4, which is not great if you talk about elections. But you could see, for example, in the confusion matrix, what kind of images were getting correctly classified, and you see a lot in NIST. But for example, you see a lot, not a lot, but several errors in a true 9 that it gets classified as a 4 because some people close a 4. So sometimes the computer struggles to differentiate or like distinguish what a 9 is and a 4 is. Okay, so that's why it's important to also look at these confusion matrices of the time. When you predict the numbers, you can see that it did very well, right? In predicting at 2, at 3, at 6, right? But with the CNNs, there are some things to remember. One is overfitting. So we are talking about training your data and how important it is to give accurate labels, to think about what kind of data you're using and what kind of patterns you want your model to learn. But there's also something that if you give them too much information and you let the model learn a lot from that data, then it learns so well what they have that then it's really hard to import it to new data. So it learns everything that it needs to know from your training data. And once you give them another sample, they focus on the things that were exclusive to the training data and not on the new ones. So we need to be very cautious about that. And the ways in which we deal with overfitting is to increase the number of training images all the time, use data augmentation. So the algorithm or the model doesn't focus on local particular stuff. We're gonna see data augmentation in practice once we go to our CNN. And then also drop out random neurons sometimes that might be learning very local or specific features of the training data. We need to optimize our training set. This is called basically active learning. So how informative are the images that we are using in our training data and how representative they are about the topic that we are, or the object of interest that we want to classify. So this also means having a balanced training sample, including many images that like if you want a particular topic, you just can't have 3 images of one and 100 images of label 2. Like you need to have some balance there as much as possible, or at least enough samples so the computer can really learn the differences between them. And we're also going to see an example of how not having these might have some issues. Try to denoise your images. We're also going to talk about how we can normalize them and manipulate them a bit so they are cleaner. And just be very cautious with bias training. So as I said, we generally tend to think that the computers are unbiased because, of course, they don't have an ideology or an agenda to follow, but we are feeding what they need to learn, right? So you see all of these examples. Google had some problems, for example, with identifying African-American or like Black people in general in the pictures. And sometimes their algorithm was confusing the identification with animals. So it was such a hard task that they had to remove the label of certain animals in the algorithm because they were doing horrendous mistakes. So this is because sometimes you're not using enough samples of your interest because you are not using enough coders with different perspectives or different ideologies to really classify different things. So it's important to remember that the training stage is probably the most important when you're using these tools. And that involves, expanding or giving diversity to your pool of coders and classifiers, doing a lot of like pre-validation of the labels that you want to see in your data set, checking the confusion matrices and the intercoder reliability between your coders to really make sure that you're tapping into the things that you want and how you can decrease bias. And another thing is that people generally tend to use these tools, get a classification and be like, okay, that's it, we're great. But again, this is not replacing your human work. Sometimes you even need more work to really know what's in your data, what's happening in there, the testing with out of sample, making sure that you're measuring what you want to measure and whether it's working properly. So validation is super important. Checking mislabeled examples, right? That's always something that really works. Where are your errors coming from? Learn about your mistakes. Learn about the problems in your sample. This is not related to CNNs, but I always give the example that when I was initially running the bag of visual words and the STM in my images of the Black Lives Matter movement, I was constantly finding a sandwich topic. And I was like, why am I getting a sandwich topic? And the sandwich topic was coming from publicity and ads from Subway that getting like that like the scraper got from when I was getting the images from Facebook. So of course, that one is very obviously wrong, but it's always important to go back and know your data and know what kind of things you're getting from the results in a more qualitative way, and use as many diagnoses, accuracy, loss, plots, etc. Okay. So the final thing I'm going to say before going to our break is what's transfer learning. And it's actually incredibly intuitive. So that's the reason why I don't have a long explanation. We're also going to see it in practice in our session. But the idea is quite simple. And it's like, this was the original network that I showed you, right? With the different layers and the full process. Here was our input image transformed into a matrix. The filters, as you can see, a lot of filters in the first layer, creating a feature map, getting through the activation layer, getting to the pooling layer, and finally, the hidden units were those weights or coefficients that led to the outputs, okay? Now, this is suppose that you're interested in 10 labels from 0 to 9 as your outcome, as your predicted outcome. With transfer learning, the idea is that maybe someone trained a really sophisticated model, not this one is quite simple, but a really sophisticated model on millions of images, wink, wink, Google, Amazon, Facebook, right? They train them, and then you don't need to go through that process because the model already learned a lot of features and patterns from the images that they used. But you are interested in a completely different output, or maybe in something way more specific. So let's say ImageNet, ResNet 50 was trained on ImageNet, this like big data set with millions of images with 1,000 categories. But you're interested in detecting whether there are bees or ants in a particular image. So then you don't need the 1,000 categories. You really just want to fine tune the actual network to those outcomes of interest. So if you want to do that, then with transfer learning, what you do is that you freeze some of those layers. So in this case, for example, we're going to freeze all of these layers here that already went to training and already learned a lot. And then we're just going to unfreeze the final layer and retrain it with our data of interest. So ResNet, which is this architecture, learned a lot from those ImageNet, detected some patterns. And now we're going to say, wait, but I don't want you to find the weights for the final output with 1,000 categories. Now I'm going to give you 2 categories, ants and bees. And I'm going to show you a lot of pictures of ants and bees here. And now please just tell me the new outcome, whether there is an ant or a bee in this picture. Okay, so the nice thing about this transfer learning thing is that you can use all of these costly and very complex architectures, and at the end use not so much data, new training data to have the outcome of interest. So some of the social, not some, all of the social science applications that you see from Zach and Jung-Suk, from Andrew Casas and Nora Webb-Williams, they are using these CNNs with transfer learning, where they fine tune based on what they need, and they are not using a lot of images. Sometimes even a couple hundreds are enough to really get good results. So that's a really good advantage, right? Like, you no longer need millions of images to train your CNN, but you might need 300 images to retrain it and get accurate results. Okay, so that's transfer learning, and that's actually the way to go, because these pre-trained networks are available in Python, in multiple libraries. It's actually quite easy to get them, and a lot of people are already creating them. So Zach has like this great architecture to detect protest and violence in them, or object detection in social movements, and it's already a pre-trained algorithm that you can also, again, like import and use your own pre-trained data for a particular objective. So we're gonna go through it in after the break. Just an example, actually an example that fails, but that's a spoiler alert. Yes.
Just a quick question. Does transfer learning lead to overfitting?
Those transfer learning, well, any of these can lead to overfitting, right? Like any of these can lead to overfitting if you are like letting the model run for too long, if you're not using high quality training data. But no, it's not a feature in itself of transfer learning to lead to overfitting. And this is mostly because then at the end, the model still needs to learn something new, right? So it's gonna still take some input from a completely new type of data that it hasn't seen. So in a way, it's actually learning from scratch those parts, or like the last stage that it needs to fully achieve the main objective of the new model. So it could still happen if, again, like you do the things that you would normally do with a CNN, but it's not a feature of transfer learning. Another thing that it's important is that here I am just freezing the last layer, which is the fully connected final layer that just like alters basically the final outcome. But you could freeze much earlier layers. In this case, again, it doesn't make a lot of sense because it's basically one activation layer. But if you have like ResNet has, you'll see it in a bit, like 200 layers. So you can, no more, like 250. And you can freeze early layers and then really modify or customize the rest of the architecture of the model and retrain on your data. But that's going to be depending on what you want and what you need for your own purposes.
Michelle, we have one hand raised.
Okay.
Yeah, I want to come back to the transfer learning and overfitting. Because you do not know the images used to build the model, to train the model, and you are not sure that the image you have to predict now was already been used for the transfer learning purpose. So maybe it will lead to a wrong prediction. I don't know.
No, that's an excellent point. And in that case, it's true. But this is exactly why transfer learning, probably my example of bees and ants might not be great, because actually ImageNet has bees and ants. So probably you should just use it and get the highest probability for those images, and that's it. But this is definitely where you need something more customized, and you have like a pretty good idea that those training images that you're going to use, the new ones, are not going to be in the big data set. And because these are trained in very specific data sets like ImageNet, for example, it's not that you are not going to know by heart all of the images there, but it's a very specific set that probably is not going to overlap with your set. But that's a super valid point. And actually something that I was going to say that it's inspired by something that you said, although it's a bit unrelated, is that like, this is crazy, right? Like sometimes I was so skeptic about transfer learning at the beginning, because it's like, you're telling me that you're training your sets on cats and dogs, and then you want to identify protests. That sounds like a no-go to me. And I'm still kind of skeptic. Like I will still try to find like a model or a pre-trained model that has been trained on data that is closer to what you want, even if it's not exactly the same, but at least semantically similar. So then to apply the transfer learning and get good results. But there are some studies, and there are studies that say, yes, do that, because sometimes it fails miserably if your task is really ambitious. But there are also some studies that show that even with this crazy training on dogs and then classifying landscapes, it kind of works, which is a very interesting and amusing feature of transfer learning. But did I answer your question, Didier?
Yes.
Yes, you do. Thanks.
Okay. Okay. So if there are no more questions, I will suggest a break here. I have a few other things that I want to show you about the Google API and just a wrap up of this part before we continue to the practical block. But if there are no more questions, we can take a break and continue in 15 minutes.
No more questions, so we're good.
Perfect. So I didn't talk that much with a lot of detail about CNNs as with Baba visual words, because I feel that all of these things become way more obvious when you are doing them in practice. Like it's less, the Baba words is, okay, look, this is happening. This is a gradient. This is how we understand what's happening. But here it's more like how to build, like now you know what layers are exist to build a CNN. But it's not until you go and actually do it that it's like, oh, okay, this is how we are stacking them to create something. So that's the reason why I didn't talk that much, but we will review a lot of things now with the practical code, if that's okay with you guys. Okay, so I'll see you 12:25, if that's okay. Okay, are we ready? Perfect. So now I will share with you this is the notebook, the Google Colab notebook that I created for the class. I have to say though that it's the first time that I'm using it. It's just that I thought that for like now this webinar with that many people, it would be the easiest to follow. The thing is that and Alex has struggled with me even for a class that I taught at Rice, the computational social science class. The thing is that some of these things that we're going to use, the installing them probably is a bit, it's probably the hardest part sometimes. And it highly depends on what operation OS system you have, right? Like what kind of computer, the versions that you're installing and everything. And I use Linux and I use Mac, but for example, I have no idea about how to do these things in I forgot the name. Well, in Windows, I completely have zero idea. So the thing is that in this way we can kind of at least have an idea of what's happening. You can see what packages you need. You can see how things are supposed to work. And then Stack Overflow is going to be your best friend when it comes to like really adapting some of the things for your own projects or for your own particular setup. Okay, we will still be very happy to answer some of your questions that you have, and we're going to do our best to answer them. But just so you know, there are some technical stuff here that probably we will have to Google it too. So again, in the Slack channel, if you contact me, I will do my best. But you will find also a lot of help and support in Stack Overflow and other forums dealing with computer vision and Python. So I'm hoping I tested this, and we tested this particular notebook several times, but there are some things that will take some time to run just because it's using some computational resources there, and because we're dealing with a lot of data, and some things might not work at the end. But let's cross our fingers, or how you in Germany say, let's higher our thumbs and hope that this will work. And I will just appreciate if you're a bit patient with me in this case, because again, this is also new to me. This is an experiment. We're all learning something new. Okay, so I created this, and I actually mounted my Google Drive, which only has data for this class. But if you're having issues when you try to mount it or something, I can also share the links for the training data. I can also share the links for the files that we're going to use, and then you can upload them in your personal machine or mount your own drive and import all of these things to your own computer and see how it works. Okay, but for now I'm mounting it and hoping that it will work. Okay, let's see. It's not appearing here, you see. Just give me 1 second. Okay. Okay, let me stop sharing for a second. I'm sorry. Okay, now let's go back and share this with you guys. I'm so sorry. Okay, now we're ready. Perfect. Okay, so we're gonna import a bunch of libraries and things that we need to run our first CNN, okay? First of all, we're gonna need, in this case, TensorFlow. There are multiple things that you're gonna see you can use to run your CNN. PyTorch is another one that it's pretty popular. Keras, this is like a combination of TensorFlow and Keras. Theano is another one. I find this particularly good and intuitive and efficient enough. But if you have like really big projects, then people suggest Theano. If you really want to make it more like intuitive and easier to understand the code, then PyTorch is a selection for everyone. But at the end, they all share a lot of similarities. So don't stress too much about it. And let's see. And the important thing here is to like really learn the intuition between what's happening, or like what's happening here with the stacking of the architecture, right? So we're gonna use TensorFlow again, a Keras as a backend there. And in this case, for example, what I'm doing with import from these libraries or these subfolders in the library is to import the different convolutional layers that we are going to use in our architecture. So that big thing that you saw when I show you the CNN, that's called the architecture of the network. And the different layers that we are using are here. So sequential is just to say that it's going to be like this network that is going to learn also to predict the final outcome in a forward fashion. Comp to D, it's going to be a convolution layer. Max pooling to D is going to be a pooling layer. Here you have an activation layer. Flatten is just going to put the matrix into a vector, which is like necessary to do the final predictions at the end. Dense is going to be the final layer that we're going to use to define our outcome, and that is going to be the one that learns and gives you the final classification. Dropout is to drop some neurons along the way to avoid overfitting, for example. Zero padding, and I didn't talk about padding, and I should have. So zero padding is like, remember that we said we're going to slide these filters along the image. Something that you might have noticed is that, what's going to happen at the edge? For example, in pixel number 1, what are you comparing, or what are you like, what mathematical operation are you doing if you're out of boundaries already, right? So for some people, it's actually important to still do some mathematical operations along the edge, because the edge actually might have some important information about the image. So if that's the case, we do some padding, and padding just means appending like some zeros or some ones. That's why this one is called zero padding, because you append like an extra frame or border to the image with a particular number, like 0, so you can at least compute the convolution at the edge, and you have some numbers there. Otherwise, it's not going to be possible. So your image is going to be reduced even further, right? Without the zero padding, because those edges, especially like 2 layers in general, or like two rows of pixels, are not going to be counted. Okay, so that's the term padding, and that's the layer that we're going to use too. Input is to define what type of images we're going to get, something that I didn't mention, and I'm telling you, like, this all comes when we are already practicing. It's going to be that because, as I told you, matrix forms are really helpful for optimizing and making computations way more efficient. They are like faster. Like if you think about a dot product in R, for example, it happens in 1 second. If you try to do it by hand using vectors or using the different items separately, it takes 1,000,000 years. But matrix multiplication is really efficient. So in order to keep or to take a full advantage of that matrix multiplication, it's always better if you work with square images. So it doesn't mean that your images have to be square. It just means that we will have to resize them to have the same width and the same height, so they work better as input for the convolutional neural network. Okay, batch normalization is also like a process, or like not, it's counted here as a layer, but it's like just like steps along the way to make the process more efficient, to work with like little batches instead of like the full network, learn at different stages. So the process doesn't take as much time to run, for example. We're not going to use that one actually at the end, lambda, but this is just to map functions. And then, for example, here from the optimizers, we're going to import, there are different optimizers, like we saw the steep gradient descent, for example. We're going to use Atom. The Atom optimizer is really good because it's more dynamic in the way that it adopts and changes the learning schedule. When we are exploring this multidimensional surface that we talk about, Atom is much better, and you need to do less tuning than other optimizers. So that's like a standard in CNNs to use it. But you can also, like, there are a lot of papers that review the differences between the optimizers. So if you feel that one is more suitable to your needs or to your particular question, then you can use a different one. And in this case, for the transfer learning example, we're going to use ResNet 50. That architecture, again, it's like super big. You're going to see it in a bit. And you can, the nice thing about TensorFlow and Keras as a package in Python is that you can import multiple architectures and multiple weights already, or coefficients already loaded into them. So transfer learning becomes way easier. Okay, and then we're going to import some extra functions that are going to help us to pre-process the input, create the data augmentation, transforming images to arrays from NumPy that make the process way easier, that help us to binarify our labels, and to even give us a diagnosis. Okay. And and here others that also help us to read the data that we have. Okay, so I am going to run this. Here, I'm also telling that I want to use the GPUs that come here in Google Colab. So here it's going to tell me or give me the diagnosis that indeed there's a GPU that will be working and will be making the computations way faster. Okay. Okay, now I mounted my my drive just to have it there because I have my training data for the second example, but we're going to begin with a really simple one. Okay, and this simple one is going to be the one that I talked about in the slides about detecting or classifying handwritten digits. So this is going to be the textbook example using the MNIST data that is like really clean and nice, just so you guys see it in action and see it like very clean, how cool it can be, right? So here we are going to load our data, and in the package MNIST, we already have it. Again, it comes in many packages for computer vision and for deep learning. You already have those models and even the training data. So in this case, we're going to load the MNIST data. And the way in which this function loads it is that it's going to give you all the matrices for the numbers for training and for testing, and all the labels associated with each of those matrices for training and for testing. Okay. Depending on what backend, either TensorFlow or Theano, what I told you are using, the image data format is going to change. Sometimes the channels are going to go first, and sometimes the shape is going to come first. So with this, what I'm trying to give you is like two conditional statements that will just transform and reshape your images based on what you have without you having to specify it. So if it detects that your backend has channels first, it's going to reshape all of your numbers, all of the images of these numbers in our training and testing data set to size 28 times 28 pixels. These are very small numbers, right? You can imagine. Originally, the MNIST data comes from where it was motivated and then created with the idea of making the handwritten letters and numbers in post, in like letters and post automatically detected by the computer to help with the distribution of post, mail post in in the UK, I think. So that was the motivation. That's how they created the data set. So now it has a lot of samples of numbers coming from addresses and a lot of people writing them. Okay. And then we're gonna scale the data to make it fit into the range of 0 to 1. That's why we're dividing into by 255. That's like a common convention that we're gonna do with most of our images as part of the process. And then in this case, we're gonna, so here our labels is like, here is your image, right, of a 3, a number 3, and the label is gonna be a 3. But the way in which we are gonna have this multi-category classification, it's basically gonna be, in this case, 10 numbers, right? So it's going to be a long vector indicating whether, like binarifying it. So the first column is going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then you're going to, if it's a 3, then the fourth column is going to have a 1 and the rest of the column is going to have a 0. So we need to do this to actually make the input compatible with the output that the CNN is going to give you. You're going to see this is because CNN or like your model, what it's going to give you is not actually like, oh, this image has a dog or this image is of a 3. It's actually going to tell you, hey, there's a probability that this image is a 0, a 1, or 2, or 3, blah, 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 blah. Or there's a probability that this image is a dog, a cat, blah, 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 based on the labels that you are interested in.
Michelle, I think you're muted.
Yeah.
Sorry. Sorry. Of course, it has to happen to me every single time that I use Zoom, even after 2 years of using it. Thank you. So here I'm just printing the number of classes, right? 10 classes from 0 to 9. And I am also printing now how the new testing labels look like. So what I was explaining, this is going to be each row in this array is corresponding to one image and its corresponding label. So in this case, this image, the first label should be a 7, right? Because everything is zeros except for 9, 8, the seventh number. Okay, and I'm also printing the shape of our testing array, which is all the images that we have for testing, which are 10,000 images. Remember that we, I told you automatically that's what we have in the MIST setup. And they are of size 28, and this is a number of color channels. So in this case, all of these images are black and white or grayscale, so it's about pixel intensity. Okay, any questions here? Okay, or should I count to 10 mentally? Well, if not, let's continue. So this is how we are going to define our CNN or how we're going to build it. Okay, we are going to start with some, it's really like using Lego blocks. Okay, we're gonna stack the different layers in a way that we're envisioning how this should work and how these models should learn. Okay, so if you have a task like this one, which is identifying numbers, and it's actually quite simple, even if you think about the size of the images, how different the images are, what kind of patterns are similar between them, how many labels you have. If you consider all of these things, this is a quite simple task, actually, right? Like that's the reason why it's a textbook example. So in that case, you might not need a super, super deep, crazy network. If you're interested in a much more complex outcome of interest, or you are dealing with a more ambitious phenomenon to study, then you might need a more complicated network. Where and how, like, the criteria here is, if you need to learn a lot of features to make a decision about the label, the predicted label of your images, then you need multiple layers that learn these complex relationships between the features. Okay, so that's the reason why ResNet, AlexNet, all of these have a lot of layers, trying to learn a lot from the millions of images that they have and the multiple categories. So if you have 1,000 categories, you really need to learn a lot from the images that you have. Okay, so can anyone want to take a stack at what's happening here and what kind of architecture we're building?
ResNet?
This one is not ResNet. This one, we are just like actually building like a customized network without any pre-trained or weights or pre-trained architecture. And I can guide you a bit. So we are starting with a model, like our canvas is going to be the sequential model, and we're going to add a layer in which we're basically defining what kind of input we're going to get and what to do with it. So it's basically saying the input shape should be 28 times 28 with one color channel. That's what we're going to get, right? And when you get those images, please put some padding of size 2 around the image. So it's going to put a layer of 2 pixels around, or like a border of 2 pixels around the image to compute the convolutions for those pixels at the edge. Okay, so you can define many other things, allow for just a specific type of data or extension, but in this case we are just like setting these 2 things. Okay, then we're gonna add our first convolutional layer. And this one is specifying a convolutional layer with 32 filters of size 5 times 5. Okay. And inside this convolution, we're already going to put our activation layer that it's like, once you did the convolution and you create the feature maps, please apply a ReLU function to the feature maps that we created. Okay. So now that we went through these 2, what is the max pooling doing here? Or what's the next layer that we see here?
It's reducing the total number of features so that like it's bringing the total number of features down.
Yes, perfect. So this is a pooling layer, right? And the idea is that we're gonna go like a filter is gonna go, we're gonna slide this filter through the feature maps that we have, and we're just gonna keep the number based on a criteria, right? Keep one number out of the areas that we are sliding to reduce this feature map. And in this case, we are using max pooling. So it's the one that we saw on the slides, right? Like we're gonna put that filter and we're gonna pick the number that is the highest in that area and put it in our new matrix, and then slide to the next pixel and do the same. The pool size is also the size of the filter. In this case is 2 times 2. You can imagine that if you have a much bigger filter, then it's going to reduce it more drastically, right? Because then it's going to like really condense a lot of information, or like lose a lot of information in the process. So 2 times 2 is something recommended to not go so wild with the max pooling. You can also set the stride, which is like, now I've been telling you how we're going to slide all of these filters, but I haven't told you whether it's really by pixel or if we can actually skip some and do that. That's also going to have an impact on how much you reduce your matrices. But in this case, you can also include the argument of how much you want to your filter to jump. through the image, or how fast you want it to glide, or how much you want to cover in the image to reduce it further. Okay, I think the default is 2, like a stride of 2, so it's not doing it for everything. Okay. Then we're gonna have another convolutional layer here, right? And this one is not of size 5 times 5, but 3 times 3. So we went from like focusing on like bigger features and bigger things that are appearing in our images to like being more fine grained. Like, give me a feature map of like smaller things that are happening, or like more granular things that are happening in our images, and do the same thing. Activate them with a relu function. Okay, another pooling, a dropout saying, okay, drop 20% of the neurons that are learning and are getting activated, drop that information randomly. So we are sure that these neurons are not learning very, very specific features that are just particular of this training data set. And then finally, once we have these digested feature maps at the end of this row, at the end of these layers, flatten them. So make a vector of them, okay? And then use these dense layers that are basically those with weights. So use one with 128, use one with 50. So learn something. If you use more like a bigger dense layer, it's gonna try to create more weights there, okay? And finally, give me the last layer should give me the final output, which in this case, it should have the number of classes that we define here, 10 classes, right? So give me 10 probabilities per image of belonging to each of these 10 classes, and the activation is softmax. So softmax is a fancy way of calling the logistic function that you know in all of your logics. It's just the x over 1 plus x, okay? And this is, we use this function to make sure that the probabilities that is giving you of belonging to each of these numbers sum to 1, right? So you will have a vector of probabilities per each image to belonging all of these categories. It's summing up to 1, so then you can just choose or determine what the actual classification of the image is based on those probabilities. If I'm telling you that this has an 80% probability of being a 7, then probably you can confidently classify it as a 7. These probabilities are probably yes, I think when you, I generally get obsessed with this discussion of whether of how to measure uncertainty in deep learning, because again, I'm trained as a social scientist, and I always think about standard errors and about parameter distribution in Bayesian frameworks and how to evaluate whether some things are like coefficients are reliable or not. I always think about the different sources of uncertainty, right? Measurement error, sampling error, in this case, like modeling errors. And I generally engage in discussions about this. And a lot of people feel comfortable telling you that these probabilities are the closest that you can get to a measure of uncertainty when you're doing these models. It's like almost like uncertainty and godness are fit. they interpret them as many things. And yes, it's fine to use this as a measure of how certain you are that your numbers are getting classified correctly. But just remember that they are not the same thing. Don't understand them or interpret them as we generally do with standard errors. Here, for example, changing the data a tiny bit, like cropping your image or removing a corner or removing part of it, can wildly alter the probabilities of that number. And like even removing part of information of the image that is not super crucial for the prediction actually changes these probabilities. So just don't take them as your gold standard of how good your model is at predicting some of these models. Okay, so it's just an indicator of how certain your architecture is of making some guesses. Okay, so we define our model. It's inside this function, right? I forgot to mention that you always need to define it inside a function. and then well, it makes it easier for then later compiling the model. And then you compile it, you specify the type of loss function, remember, like the error function that we want. This one is the one for multi-category tasks. You define your optimizer, and you tell, or you ask the model to give you some metrics. In this case, I'm just asking it to give me the accuracy of the model, which is going to be how the proportion of cases that I'm correctly classifying based on the training set, a validation set if you want, or if you have one, or the testing set. Okay, questions here?
Nothing so far, Misha.
Okay, great. So let's compile our model. Here you're gonna have no, so that's interesting thing. Sometimes you compile your model, you determine your functions, and once you're about to read it, then all the errors and bugs start coming up. So you will have to go back to this architecture multiple times. This is again trial and error. Okay, so here we are initializing our model based on the function that we created, right? And then we're gonna fit our model, right? And we're gonna fit it to our training data set, right? That's how we're gonna learn, the model is gonna learn. Here are our labels of interest from our training data set. And then we're gonna use the testing data set as a validation step. So the accuracy that we're gonna get is gonna, the accuracy is gonna be based on the training set. If you want the validation accuracy, then you need to put val accuracy. Okay, and then we're gonna go define the epochs. So the epochs are the number of times that that the CNN is gonna go through your training data set. It's gonna review the training set. So remember that I told you that at first we're gonna reduce all of these feature maps, and then based on that, it's gonna make a guess about the weights or these coefficients of those features for the actual classification. And it's gonna say, I think this is a probability for each of these images that you gave me in the training set of belonging to these categories. It's gonna use those probabilities to assign them a label, and then it's gonna compare those predicted labels with the true labels that you gave in the training set. And it's going to take the difference between them to calculate the error. Take the differences, sum those differences, and that's going to be the error. And it's going to be like, okay, I'm very far. It's a large error. Let's try another set of weights. So it's going to go back again. That's the back propagation part. It's going to go back again and see how changing one weight alters the full network. And it's going to estimate the error and be like, oh, okay, it's getting lower, then I will change this one now. And it's gonna like start changing all of these weights until it finds, after several iterations, the minimum weight according to a criteria that you set, right? Like once the error is this small, stop. Or once the derivative is not changing that much of that error, stop, right? So the epochs are at least gonna go through this process or these iterations like several times, and in this case 15, but it's important to know where to stop. Like it's always like really easy to say like, well, if the model is seeing my training images, if the model is learning from them, I should like keep learning, right? Like I should like let it run and let it learn. But this is related to overfitting. If your model sees those training images over and over and over again, yes, it keeps learning, but it keeps learning these specific features of this training set. So then at some point it's going to think that something that is very particular to this training set is really important to the predictions. So if your testing set or your out of sample set doesn't have that characteristic, then it's going to be really confused. And it's like, wait, but I thought that was very important. And then the accuracy might drop drastically. So we're going to see, or we're going to have like some plots to see when we should stop, or when overfitting is not like you don't get a number that, oh, now I have overfitting, but there's a way of like tracing it or like starting to suspect that you have overfitting. Okay.
Michelle, are those diagnostic plots how we determine the number of epochs, or what's the like rule of thumb of determining kind of where to start with the number of epochs?
I will always get like I will run like start like with very low epochs. Some people, I recently saw one with like 3 and 4 epochs. And for example, now I got one with 6 epochs, which for the task is actually very, very low. And then, yes, you have these diagnostic plots that we are going to see and check how the accuracy and the loss function are both behaving as the number of epochs progresses. So at some point, the accuracy generally tends to improve, right? But you even see it in your CNN. We're going to see it right now, that sometimes it jumps from one epoch to the other. It jumps dramatically. And after that, it gets like stagnated and it stalls. So in that case, it means that it's still improving and it's still learning stuff, but probably not learning more substantive stuff that it's improving the predictions dramatically. So when you see that in your training set, the accuracy keeps improving, but for example, in the validation set or in the testing data set with the same number of epochs, the accuracy is not improving anymore, then it means, or it's a good sign, and the plot is telling you that it's already learning too much from the training set, but not from the validation or testing set. So probably that was a very long and complicated answer for yes, the diagnostic plots might help to determine that. All good?
Yes.
Perfect. And here with the batch size, again, like sometimes what you can do is to define how many, instead of like telling the CNN to look at your entire pool of images all the time, you're like, okay, sample a random collection, a random batch of 200 images and just look at them. And in the next, and like do it differently and come up with a solution for all of these batches, and then tell me what you're seeing in these different batches. Also with the idea that this can help to make the process more efficient, faster, and a bit cheaper than if you are letting the full network learn every single time. And it also helps to learn different stuff from the different batches and to avoid like freezing the model. Like, oh my God, I have too many things to look at. I don't know. It can definitely get stuck, so to say. Okay. So let's feed it and let's see how it works. So it's initializing these. Like now, for example, it's going to start with epoch number 1 out of 15. 15 was probably an overkill for this particular example. You'll see why. But I will always try. With CNNs, it's always good. And there's something called deep ensemble, when you can just like run multiple models. There's also like hyperparameter grids, where you can change different parameters of your model, the number of layers, the size of the filters, the batch size, the epochs, and everything. And it gives you, for those different combinations, what's the accuracy for the training and validation set. So you have an idea of which one is the best model. It allows you to pick the best model based on different combinations of parameters. And those deep ensembles and hyperparameter tuning grid searches are phenomenal for like at least have some peace of mind that you're doing something right.
Michelle, does
Yes.
the batch size always equal? Does the batch size have to equal a number to which is some power of 2? Are there constraints on what the batch size can be?
It has to be, yes. The only constraint is that it calculates also, you can also review certain batches per step. So it depends basically on the size of your training data. If you have a lot of like potential combinations, or if you have, like Python lets you know, like if you put a batch size that it's too small or too big, it says like there's an error. The batch size has to be, and they have even the formula of you can't exceed this, for example. Because I don't think they have resampling. So there's a limit on the number of like blocks that you have based on the size of your training data. Okay, so now you have here some like descriptives of how the, let me how the different metrics are working, right? So it's telling you how the loss function, remember we want smaller losses here, meaning smaller errors. It's telling you the accuracy, like the percentage of correct predictions in your training set. And then you have the validity loss and the validity accuracy, which that one is important because it's taking, in this case, the testing set. What I generally do, and I'm not putting it here, is that I have a training set, I have a validation set for this particular purpose of like running the epochs, and then I have an extra testing set when once I find the perfect, not perfect, but a very good model, then I chose one and I feel confident with that one, then I finally apply it to the test set to really report accuracy and all the metrics that people are interested in. Like I use the validation to tune the model and find it, and I put it to the real test with a testing set. That's what I generally do. And that's what I'm saying here, that sometimes you see that the validation, the training set keeps improving. But when the differences are so tiny in the validation accuracy, then you need to stop. Here you can see that the loss function was kind of high and the accuracy was not great, right? Well, great. 0.9 is actually pretty good, but in this case, it was not amazing. And it quickly jumped to 97, and in this case, the loss dropped dramatically. So this is just one example of how with 2 epochs, like with 3 epochs, we would have achieved already really decent results. But if you keep improving it, then you just marginally improve the full model. Okay. And here we are just like telling the model to really evaluate and give you the final answer regarding the testing data, and it's giving you, the accuracy is 0.9907, which was the last iteration here. In this case, I would have used another testing data set to get this number, and that's the one that I will report in a paper, for example. Okay. So we can check some diagnoses here. In this case, to predict the test data set, to get the predictions, and then get a classification report of what particular, like this is like a report. It's a nice function that I think sklearn has, one of the libraries has, that it's like a structure or like more organized version of a confusion matrix regarding the tests that you have. So in this case, I will actually run it separately. Just give me 1 second. I will show you how the raw predictions look like, because remember, what's the output from the CNN? Probabilities, right? So this is going to be an array with all of these probabilities per image in our testing sample, right? And as you can see, the first row, it's this row of 1, 2, 3. Well, we can actually. Okay. Oh, sorry. Okay. So this is how the first row looks like, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 numbers corresponding to the probability of belonging to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So then, because we're going to have these vectors for all of the images, we need to define what's the maximum probability, and then get that, get the index, or like get the category to which that probability belongs to. Okay, but you can see that the length of these predictions is of size 10. So in order to extract what the maximum is, in this case, we use argmax axis 1. It's going to go through the full array of predictions and then get the maximum probability there. Okay, and then it's gonna, this is the real arguments, right? And in this case, this is the prediction. So it's gonna compare the real labels from the testing data set with the predictions that we got in the previous step, and then it's gonna give us the classification report. So as you can see here, it gives you the different metrics that you can have and that you generally report in a paper, like precision, recall, the F1 score. Support is also like how many numbers you have in your testing data set. And it gives you how precise you were in detecting some of them. This is way more informative than just getting the accuracy of the overall model, right? Because if there are some mistakes in one category is like trickier than others, or one is not working as expected, this is the way in which you can definitely detect what's going on, right? And you get much more information about what's happening. And again, because this model is so neat and so clean and so awesome, you have incredibly high levels of precision here for all of the labels here. Any questions?
What could be reasons for getting poor accuracy when using a CNN?
Poor accuracy? Well, so this is going to be related, for example, to what I mentioned briefly in the slides, that your training data is not fully identifying or is not super consistent across the labels that you are interested are not super consistent in your training data set, right? Like maybe there are images that look alike or that are very similar in terms of the features they share, and turns out that they have very different labels, right? So then the computer gets really, really confused and outputs really small probabilities of belonging, or like here, instead of 0.9 of belonging to a 7, it's like 0.4 and 0.5 between two categories, right? So then like those differences can lead to very, very dramatic changes. We will see actually in the next example when we're going to use faces, and these faces have some manual annotations on whether they look happy or mean or attractive. And the accuracy is really, really low because the model is just not able to really find the small features that distinguish one phrase from another. Okay, I mean, it's a very small architecture. It's using not so many like very distinct images, for example, that could really, like, it's not super obvious that this is a super happy face and what the features are versus kind of happy, kind of sad face, right? The input that you're using to train the model is not very convincing or very informative for the computer.
Someone else asked or commented that they noticed that you didn't do data augmentation. Isn't it a good thing to do based on the quantity of your data?
Yes. I didn't do it in this example, but I'm going to do it in the next one. And yes, that's really nice. This one is because, again, like it's just like almost like a toy example, this one with like, look, it's very simple. And as you can see, because the precision and everything is so good, you definitely didn't need a lot of manipulation out of the data or a lot of different samples to really learn the important features from the data. But you will see that in the next example, we're going to do the data augmentation. And for most, if I would even dare to say all of the applications that we as social scientists have, most of them are not going to deal with like handwritten numbers. So for most of those that have more complex images, for sure do data augmentation. I think someone raised its hand. Didier, I think.
Yes, I raised my hand. Thank you. For the question about the poor accuracy, you said that it should be the quality of the data. Maybe you build your network from scratch. Don't you think that it could be quite difficult to get a good network by your first time, by doing on your first time? I don't know. Any network could be good. That's my question.
No, absolutely. It's very hard. And that's what I say, like, especially if you're building it from scratch, your accuracy is going to be so low. I'm predicting that. It might actually be that you guys are geniuses and you make it work super fast. But, and it's because you need a ridiculously high amount of data to really train a very solid model. Again, like teaching the computer to find those patterns and find those features that are defining your labels is very complex. And we're talking about tasks that are not that complicated, like detecting whether this is a bear or a tiger, right? And even for that, you need millions and millions of data to really make it work if you're training it from scratch. This obviously gets heightened and it's even more complicated if you want to detect violence in protest, right? Like then you have like this almost abstract, complicated dimensions of interest that can be really tricky to correctly predict, and that can be tricky to teach the computer. So so I agree with you. This should be really hard. And I'm like, and I generally refer to the training data as part of the main problems, because I really think that this is like, that's the core of the model, right? Like how the computer is learning is basically on that. But of course, it could also be that you just have a really bad model, that like this CNN should have more layers, that you are not learning the right features, that you need more training time. But most of the time, it always comes back to what are the images from which the model is learning.
Yeah, thank you for the answer. I have a quick question. I noticed that all this process is to achieve a dimensional reduction because of the model. But why don't we use the regular one like PCA? We can use that. We have matrix of numbers. We can use PCA to get to achieve a dimensional reduction and train the model. Why it's not working in this way?
Yes, no, we could do it. And I think that's actually how this field started. PCA is one of the first like methods that you even like now in textbooks you review as a potential way of like detecting some patterns in the pixels. But it's just, again, like, because like sometimes even like the combinations of pixels in their own didn't make a lot of sense. You needed some structure into what things to find, right? And the fact that there are so many filters embedded in these networks looking for some actual features or actual combinations of features is really powerful, because then it allows you in a way to kind of like give meaning to the things that you're seeing in the image. Like as a human, you can describe them and you can find some objects, for example, and enumerate them, but it's really hard to teach those things to the computer. So if the computer is like finding these combinations of lines and textures and finding them meaningful, then you really need to associate those things to a label, for example, and this learning process becomes more important and way more accurate. Like the studies that compare some more rustic methods like PCA, or in this case, even the bag of visual words to CNNs for these predictive tasks, just like they lose the battle really badly. Like by far, these deep learning techniques are the ones that achieve the highest accuracy.
Okay, good. Thank you.
Okay, so now what we're going to do, another interesting thing is like what Alex mentioned, like these diagnosis plots that could like give you an idea of how the loss function and the accuracy are working in the training set and in the validity set, in this case the testing set. And this function, I am taking it from PyImageSearch Gurus, a website that specializes in computer vision, run by Adrian Rosebrook. The link that I share with you about how to install OpenCV in multiple platforms is exactly that website. They have fantastic tutorials for deep learning and for for image analysis. So I will highly recommend it if you have a very specific application. They have a lot of cool ideas, and they have a good community answering questions to help. And I'm borrowing that function from them, so you can plot the training versus validity loss and the training versus validity accuracy. So again, you see, remember that big change that we saw after one epoch? It's like here, and then you see how the accuracy keeps improving, right? Like now we can see it here more visually, but the validity accuracy from the testing set remains super stable. So the model keeps learning and it's like going there and getting more accurate. But if it's not getting more accurate in the validity set, then just drop it. Like keep shorten the epochs. Okay, and similar with the loss. The loss is always going to continue going down, even if like really slowly. But if the validity loss just stays the same, stop. Okay, so this was the toy example of how the CNNs work. I hope it illustrated the main points. Do you have any questions? Again, it's a very reduced, simplified example, probably been a bit dumb. Although I will have to say that recently I actually have talked to people that I always thought that this was just like really an illustrative example, and that only Francisco and I were interested in detecting handwritten numbers because of the tally project that I told you about. I know some people are like, hey, I have a lot of these archival documents and they have handwritten numbers or they have handwritten text. Can I do something with them? It's like, so actually it could be interesting for data collection purposes. But as you can see, it's a very, very easy example. And my objective was just so you could understand the moving parts of the architectures.
And Michelle, correct me if I'm wrong or not remembering correctly, but isn't the website pyimagesearch.com? That's
That one.
perfect.
Thank
I'll
you.
post a link to the main website in the chat.
Thank you. Perfect. Yeah, I see there. Okay, perfect. Okay, so now let's jump to an example more like the ones that we are interested in as social scientists. So this is related to a project that Alex and I have, and where we are interested in analyzing what features of an image are determining the behavior or the emotion that the faces in the picture are depicting. So this was the first pass that I did at the data, and it didn't work that well. So that's the reason why I wanted to put it as an example, and it's related to Didier's question of like, well, we need to learn a lot from these images so we can fine tune the model, so we can collect more data, so we can go back and revisit the labels that we are using to train our models, etc. if we notice that something is just not working that well. So here I have a CSV file with the file name of the image and then all the attributes that humans coded about them. So I actually can share that with you. I will show it to you. You actually need permission, special permission from the authors to use that data set. So I can't just share it so publicly. But I can show you how the CSV files look. So I created a training and a testing set. Oh, just give me 1 second. Dun, dun, dun. Okay, I need to share my screen differently. Well, it's taking a while to open the CSV file, but I will show it to you in a sec. Oh, here it is. Okay, new share. Okay, can you see it?
Yes, we can.
Yes.
Perfect. Okay, so this is the file name of the images that I'm interested in. And then some people, or like several coders, basically identified or gave scores to those pictures based on these characteristics. So give me, how boring does this face look like? How confident, how egotistic, etc. And they give you a lot of scores for those things. I honestly think this is a hard task. I wouldn't know how to determine whether a person looks unemotional or humble or interesting, but I think it's an interesting task. And at the end, they gave you a score, and these are the mean scores for those faces according to each of these dimensions. What I did is, because I don't want to train now a continuous classifier, but I'm more interested in actual categories. What I did is just to round those numbers. For some of these characteristics, we're going to focus on how happy the faces look like. And at the end, it's going to have 7 categories, from 1 to 7, where 7 is the happiest and 1 is the least happy. Okay. So now here. And you can actually see, this is how the faces look like. These are the images of the faces. So also like quite standardized. You see the oval with the frame, and it's like a close-up, not a lot of like really variation in how they are presented, which is always nice when you're dealing with it. Okay. So now, here I'm importing the CSV file with the training images and the testing images. It's imported. I can't remember. I think the training set had 1500 and the testing set had around 500 or 485. So that's the shape of it. Then I'm telling to get a resolution of 256 times 256 pixels. Okay. And here I'm going to start importing. So in our previous example, we just grab our training data set and our testing data set from, from this preloaded model. Here we need, when we have them in folders or they are in our local computer, we need to do a bit more manipulation, right? So in this case, I know the path or well, the name of the file, right? And I'm going to use this function that I imported at the beginning to basically load the image, transform it into an array, and put it into a big array. So these trained images is going to be basically a big array where each entry is going to be an image. And what does that mean? Each image is basically this matrix that we saw, right? This matrix with 256 rows and 256 columns, okay? And I'm going to make sure that it's all in NumPy array format to work with it. And in this case, I am importing from the CSV files the label happy, because that's telling me the classifications I want, and I'm transforming it to a list. And then making those numbers from 1 to 7 that I show you into characters, because that's how the CNN takes the input. And I'm going to do the same for my testing images, also drawing the names from the CSV file, drawing the labels from the CSV file. And when I do this, I'm asking to print the shape of both the train and the test data sets. So this is going to take a while because it's importing the images. And that's a lot of work with the 1500 images, but let's just wait a bit. Meanwhile, it's probably a bit too early to ask questions, but shoot them if you have any.
Well, yes, it's true. We can't import this file, so we have to watch you do it, correct?
Probably. You couldn't mount the drive, right?
Well, I think I did it and I mounted though to my own personal Google Drive.
Ah,
not to yours.
okay.
I think we need your authorization code.
Okay. Okay, I can give you that if you all guys promise not to then upload weird things to my drive. Or I can share the link of the Google Drive to the images. Again, I'm a bit more hesitant now to share those because those are the ones that need authorization from the authors. So I can send you the website where you can ask for the data set if that's okay with you.
Perfect. And we have one hand raised.
Okay, go.
Just a quick one, Michelle. Did you define the size of training test samples? Or maybe I have missed this.
Yes, I basically, so in some cases, the architecture that you're going to use, and as in this case, the pre-train requires a particular or is set up to require a particular input. Here, I actually did it just for explanation purposes because I don't think that ResNet takes this particular set, but it's just to like highlight the point that it's better to use the square images for the matrix operations. So that's the reason why I'm transforming both the training and the testing set to that particular size. Does that answer the question?
Yes, thank you.
Perfect. Okay, so I don't know why this is not working.
Michelle, another question from earlier. Are there any books that you would recommend for social scientists on CNNs?
See, yes. So there's like this O'Reilly series of books, the ones that have the cute animals on the covers. This one is called Deep Learning for Beginners. I can't remember the author, but I can also let me check that. Send the link of that book. And in general, there's also like this pattern finding book, but that one is way more technical. That's the one that, for example, students like second year students of computer science take when they are taking the computer vision class. That explains a lot of like the math and intuition and stuff related to these methods. That it's pretty good. I can also send you that book. It's like the Bible for computational stuff. And for social scientists, Andreu Casas, John Wilkerson, and Nora Webb-Williams have this book from the Cambridge Element series that it's pretty good because that one is less focused on understanding the root and the statistical foundation of the method, but way more focused on the practical guidance for using them. So it's actually pretty good, and even giving you advice on how to set up Amazon virtual machines with GPUs to use a CNN. So I highly recommend that one, and they have some social science examples. So that one is pretty good, especially if you really want to have like a hands-on approach. It's also like a workshop on how to do it step by step in Python. I can write the authors. I think Nora is it. CNNs, it's from, I don't know the exact name, but you're gonna find it really Cambridge Elements. That was for Alex only, sorry. Well, Alex can forward that message.
Yes, and I found the link to it online.
Perfect,
so
thank you so much.
I'll post that.
So I don't know why this is not working. I promise it wasn't taking that much time yesterday that I tested it. Let me see if I can. Okay, I can keep going meanwhile, and then we can come back and be like, okay, what's happening with this? But we can still review the code. Okay, so here we are again turning the images, normalizing the images and making them lie between 0 and 1, just for practical purposes. Here we are doing this encoding of the train labels. So remember that now we have 1 to 7 for each of these categories of happiness. And in this case, we are getting the matrix with 0, 0, 0, 0, 0, like with 7, like each row with 7 elements, and just like an indicator of which of these elements is the one that corresponds to the label. We're doing some manipulation because I am using different functions, so you have like a wider selection of things to do if you prefer one over the other. And in this case, to categorical was creating an extra column, so I'm just like deleting that column, so the model runs without errors. And here I am printing the shape of the train images. In this case, it's telling you of one of the images, it's telling you that it has 3 color channels, right? And it has a height and width of 256 pixels. So the reshaping is working when I am setting up here with the target size. Then I'm also printing the 5 first elements of the test labels. And as you can see, at the beginning, they look like 24654, right? That's what we created in our training set. But once we made them in a binary format, it's telling you something, oh, it corresponds to this one, to this one, to this one. In this case, this corresponds to 2. In this case, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, etc., etc. Okay. Perfect. Okay, so now let's begin with the fun, right? Remember the workflow that we had, where here, when we are using transfer learning, we will have to modify it a bit. In this case, we're gonna define our input of like what kind of things the image will, or the model will take, right? It's also like putting locks in case someone is gonna use the model and you don't want them to use something big, or you don't want to use something too small. So in this way, it like limits and will throw you an error if you're giving the model something different. So we're defining what shape we want the model, the shape of the images that the model should take. And here is when we are already starting the pre-training stage. So we're going to define this REST model as ResNet, which is already imported from the Keras package. And we're going to initialize it with the weights from the ImageNet. So remember, weights mean that the model already learned all of those coefficients for all of the features that are relevant. So this model trained on ImageNet already knows some patterns and already extracted some relevant features that make some animals look like this versus how the flowers look like and what the chair looks like. ImageNet has multiple objects from daily life, including animals, plants, household items, etc. And this is how, and it already learned all of these defining features that put them in a certain category. So we're gonna, in this case, with this command, we're just gonna import it as it is, as it was trained with ImageNet. Okay. Oh, okay. This one is definitely advancing, so we're good. We're almost there. And then here, what we want to see with this command is first to check the architecture of the model. And then with this layer trainable, we actually want to see what layers can be retrained with transfer learning or not. And in this case, what do you think is going to be the answer after I imported this architecture? It's basically going to give me, for each of the layers in the model, it's going to tell me if it's trainable or not. So what do you think it's going to be the output for all of the layers once I run this command.
All of them should be fully trainable.
Actually not, because this is in this one I already imported it, right? Like everything has everything. I'm not modifying anything. I'm not freezing any layers yet. I'm just importing the model as it is. Okay, so now you saw, right? I imported my images. It's telling me that in my training set, I have 1500 images of size 256 times 256 with 2 channels. And in the validation test, I have 485. Okay, then we rescale our images.
The upper sentence doesn't have a bracket.
The what, sorry? Ah, yes, thank you. Thank you so much.
Yeah.
That's great. Okay, and here I'm just showing you how the new rescaled, the resized image looks like, and we're seeing the shape of one of the images, right? Okay, now here I already imported that model, right? So now when I run this, this is a full architecture, okay? So it has an input, it has the padding, right? It has a convolution, it has the batch normalization and ReLU, and you can see this is a very, very complex architecture, okay? Very, very complex architecture with multiple blocks, multiple convolutions, multiple ReLUs, trained in 1 million images, well, more than 1 million images. So as you can see, these required a lot of computational power to get to it. And all of this is set to true, which is kind of, like, it means that now all of them are not frozen, right? Like all of them are actually active, doing the job. Like you can use them to predict an outcome because it's fully canned and fully there. Okay. Now let's use a toy example. Here in the drive, I have some images of like 4 bears and 4 tigers. And I want to see if this ResNet that was actually trained and designed to identify objects like that are doing a good job. So I, for each of these images, I am loading it, resizing it to the target size, and the pre-processed input is doing, for example, this is another command in which we can have this normalization, and then it's predicting based on that input, what kind of animal is it. I am asking the model to give me the top 2 predictions, because remember that this res model predict is going to give me 1,000 probabilities of belonging to the 1,000 categories from ResNet and ImageNet. But they also have this nice function, decode predictions, that basically allows you to select the top 5, top 10, depending on what you want. In this case, the top 2 categories belonging to those probabilities. So I am running it. And for the tiger, I got that, yeah, there's an 83% probability that it's a tiger, 92, 74, 94. And for the polar bear, you also see very high probabilities. I can actually show you the actual images, so you don't think that I'm tricking you. This is the bear for bear 3. And as you can see, the bears are not like exactly the same. I mean, you can definitely tell that it's a polar bear. Those are the tigers. I even put that one. Which one is that one? What number of tiger 3? We can check the probability of tiger 3. Okay. So tiger 3, for example, is the one with the lowest probability of belonging to a tiger, because it's not the only thing in the picture, you know? So yes, it's giving you a high probability that the picture can be classified as a tiger, but the model is definitely not that confident given the other the other objects. Okay. Questions here? Okay. So it seems like the model works, right? Or like the ResNet as it's designed, trained on ImageNet is working. Hopefully you will believe me after these small examples, and you can see like what the output would be and how they are working. And as you can see, if your task for some reason really is about detecting very factual objects like this in your images, you see that it takes almost no time to get very accurate classifications with these pre-canned things. The problem is that as social scientists, we're generally interested in other types of questions that are not about, oh, is this a Chihuahua or a Yorkie, right? So then we need to do some extra work in that. So now let's do the transfer learning. And the first thing is that we're going to freeze some layers of this big ResNet, meaning that we're going to make them forget what they learned from the CNN, and then that they should use, or like that this new extra part, like that part that is unfrozen, that what should it have, right? Like it should learn from the training set that we are going to feed them. So in this case, for example, this is not what we're going to do at the end, but I just want to show you, we're going to repeat the same thing that we did before. Like for layer in this model from 1 to 4, 3, we're going to say, okay, make it false. So it's frozen, right? Like we freeze them. And then the rest of them after 143, they should like get activated to be retrained. So when we do it, now you see that these become false, now meaning that they are frozen, and starting with 143, these ones are all like ready to be retrained. Okay. Okay, so now this was just for explanation purposes when we want to retrain 143, for example. In this case, we're not going to do that. We're going to do something way more simple. We're going to start with our model, sequential, and then we're going to add the ResNet structure that we reviewed above. And when we say include top equals false, it means don't give me the labels that ResNet has by default. So in this case, don't give me the 1000 labels that ResNet generally has. Use pooling average and use the weights, the coefficients that ImageNet learned, or that the ResNet learned from ImageNet. Okay, and input T was the characteristics of the tensor that or the images that should be fed into the model. Okay, but because we're not including this top false, then we need to add this dense layer that determines how many categories do we want, right? So in this case, we add to this model that now has the architecture, the ResNet architecture, we add a dense layer with the 7 outcomes of interest in this case, and with activations of max, which is again our logistic regression, so we can have the probabilities. And we say from this model, set the first layer to false. Okay, so whatever they learn from ResNet, which is like now we're saying that layer, the full ResNet layer, which is the full structure, make it static, make it frozen, and just learn from the dense one. So import all of the features that you learned from ResNet. And with the new training data set, try to estimate the weights that lead to these final 7 categories. Okay, so that's what we do, and that's how we got the model summary, right? And this is an interesting parameter. So it's telling you how many parameters the model is learning, so how many weights the model is learning, and you can see there are like thousands of them, right? Okay. Questions here?
One question just related more broadly to existing CNNs and existing ways for classifying data, but do you have any experience with Facebook's Detectron?
Not with Facebook, no. I generally use the Google API, that's the one, and Microsoft Computer Vision API. Those are the only ones that I have who have their own models, the Google LeNet, for example, embedded, and a bit of ResNet for some applications. But with Facebook models, I don't have an idea. No, if you have some experience, let me know. I would love to hear your feedback or your impressions from it.
And then another just kind of point or clarification. So with CNNs, you're able to classify large batches of images, correct? Is there any limit?
Not at all, not at all. I mean, I have, for example, generally, I had like recently like 15,000 images that I had to classify, and it took minutes to get them done. You don't have any limit. I mean, the limit is going to be how tired your computer gets of predicting, but you saw that it takes 1 second per prediction top to get you there. So yes, that's the use that I generally advocate for tools like these. Is like, if you have a lot of data to label, let just the computer help you, right? Like, because then it's gonna make it really, really fast. When you are sure that your model is doing something quite good or quite decent, then use it to do these things. Okay, let's compile our model. If you have another question, you feel free to interrupt me, Alex. We're using Adam. In this case, I included a learning rate, which is, remember when we talk about how we're exploring this field in the darkness to find the lowest point in the valley. The learning rate is how extended we are in our crawling. Like, if we try to cover too much, we might actually miss the lowest point, or we might actually miss the point where the things start getting steeper again, or when the things start getting downhill, right? So, but if we do like very small steps, or we crawl to reduce, then we might take 1,000,000 years to fully explore the field, right? So, and we get tired and we get stuck and the CNN breaks, right? So we need to find a good learning rate. That's one of the parameters that you can also use. Oh, excuse me. That's one of the parameters that you can also tweak when you are doing hyperparameter search grid, and that will allow you to evaluate the models. Okay. So here is when we are doing the data augmentation for the person who asked. The image data generation function is pretty good. It allows you to do a bunch of transformations to the image. In this case, the rescaling, zooming them. So you zoom, and then that zoom of the image becomes like a separate sample. You can rotate them a bit. You can change the width, or like do some manipulations to like basically extend them in both directions. Flip them, right, horizontally or vertically. So regardless of where the face is looking at, you can still learn the important features that define a happy face. So this is this is the way to do it. And you can explore this image data generator. It's pretty cool because it's super powerful, even to import data from folders, like something as basic like that, and then do all of those transformations. And it automatically creates all of these copies from your training data using these modifications that then will be used to train the model. Okay. For the test, you don't need to do that. Remember, this is just to rescale it, for example, to make it comparable to the input. But in this case, we just need to do that data augmentation on the training set. Okay. We generate this flow to finally get everything in shape, and we fit our model. So this one is going to take it's going to take a bit, but and the reason why I put 6 epochs, for example, here is just so you guys could see it live, how it's working, and to see it finished. But if you put the epochs that needs to be there, which probably should be around 20, based on the complexity of the data and how the accuracy and validity is progressing, then we will be here for like 3 hours. So that's the reason why I put it here. And let's run it so you can see it at the end. But here, for example, I am doing some predictions, right? I'm getting the predictions from in my test data. Then I'm taking the category to which they belong. I'm printing them so you can see the different probabilities of belonging to the 7 categories. And what happened here in my testing set is that I just got 4 as predictions. And that one is because there's not a lot of variance in the labels that I used. So I have samples for all of the 7 categories of happiness, but there are a lot tending to the mid-range of this distribution. And they're not, like, my impression from this model is that the faces, a very happy face from, well, or like a 5 is not that different from a 4 or a 3. The differences are so subtle that the model is definitely not capturing them, or at least not with this training data, or at least with these labels. So probably we need to collapse the categories even more, or to expand the training set in the categories, because now they are all too condensed in the middle part of the distribution, to do other things. So this is one example where it failed, and it's also in part because the model it's not great, basically because of the epochs, and because probably it needs a bit more of manipulation for the customized architecture. Like maybe we need to add some layers or freeze early layers so it learns more. Because in this case, after 6 epochs, you see that the accuracy is actually quite low, right? It's 0.3. So it's not doing a great job at like actually predicting correctly these phases. So once we test it, it's basically doing a best guess based on the distribution of the images. But suppose that we got a really good model after diagnosis, after tuning, after changing the architecture, then you just need to save the weights for future use, so you don't have to retrain your algorithm every time that you initialize it. Then once you have the weights from a really solid model, then you just can import them, just as we did with ImageNet, and then do the prediction super easily and super fast. Okay.
So one question, what is the shape of train data gen after we do the data augmentation?
That's a great question. I actually don't know from here. But maybe we can check. I am not entirely sure. Let's see. Let's see if that has that property, because I honestly don't know how many copies from each image. Let's see if any of these two has. Okay, this one doesn't have it. That's a great question. I don't know. I can look at it. something important is that actually here, for this particular data, maybe I actually didn't need that much data augmentation. That probably that's making things worse. In an extreme case, when I was doing this, I thought about, okay, if a happy smile, if a happy face is defined by a smile, and then you do some vertical flip, the smile turns into a sad face, right? I don't think that's exactly what's happening, but my point is that actually here, the position without a lot of transformations actually could be more useful than having multiple versions of the image, right? To avoid confusion, but that's just a theory. Maybe it's not true. But once we finish testing this in a more rigorous way with hypergrid and stuff, I will let you know if that was part of the answer. That maybe in this case we didn't need that much data augmentation. And I will look for the specific command to check the size of the augmented data so I can share it in the Slack chat. Okay. Oh, Alex has some code. Maybe let me try it. Thank you, Alex. Well, there's some bug or something like we need to debug it, but we will check it. Yes, but for now, so that's all I have for you guys. I will still share not only this code, but also the code for the bag of visual words if you're interested. I just thought that this was probably way more useful for some of your applications. But I will share that. I will share the functions that I modified in R so you can run your own visual structural topic model. And of course, as Olga said, I will be happy to answer some questions as long as they are not incredibly technical or Googleable in the Slack channel. But happy to also talk about my experience, about some of the data quality process that I go through for data collection, for data training, validation, et cetera, et cetera.
One question, can you say something about image analysis in R as we've done it here in Python?
Oh, yes. So unfortunately, it's getting much, much better, but it's actually quite hard to do it in R unless you're using APIs. Now, again, it's getting better now to the point that probably will catch up with Python, but at least when I started a couple of years ago, it was basically it was very hard to do things in R with images. It would just like freeze my R constantly, and at some point I just couldn't do the things that I wanted to do. So I couldn't use the descriptors. Deep learning was like very basic, so there were not a lot of things to do. I honestly know, because I started using Python and I just have all of my code there and I learn it there. Then I just switched completely and forgot about R, which is a shame because R is my first and unique love in the world. But now I heard from some colleagues that things are getting much better and they are doing a lot of interesting things in R. Again, because I haven't gone back, like I cheated in R with Python, then I haven't come back for image analysis with R. But it's getting better. I wanted to show you though, and I can share my screen with that the Google API, the Microsoft API, all of these vision APIs that you can call from R are quite good for certain tasks. They are not my favorite for a lot of things, but if you want some face detection, they are pretty good. If you want some labels, like labeling of the image based on the objects you can find there, they are also super good. And they give you some interesting stats or like dimensions like whether there is sensitive content. So that might be some dimension of interest. So these are word clouds based on labeling, or like the labels and the objects detected by these APIs of images from the Women's March in the US. And I think it's interesting because it's a way of describing the images. Instead of using these features that we're talking about, this is like literally translating the image into how we would normally describe it, right? Like you're basically saying, this is a dog in a field, I don't know, eating a sandwich or things like that. And you're going to get some of those words. So it's interesting to see that actually they work, right? Like they tell you what you can find. And they are like quite accurate at actually doing this super factual and descriptive task. Face detection, as I said, it's pretty good. Here is, for example, you can detect the emotions that the faces have. And the results are quite mixed, but for the effort, which is almost nothing, I think at some point they start charging you per request or per query for image, but you have a lot of like tokens for free, and that pool refreshes monthly. And once you start like exceeding that threshold, it's not super expensive. I mean, it's not trivial, but it's not unpayable. So for that like minimal effort, I think it's pretty good, but it also has some errors. So in this picture, the algorithm didn't classify these faces, but this guy in the back, this one, for example, said it's a surprise face, and it looks to me like more like a sad or like indifferent face. Or in this case, they didn't classify these faces, but the one in the poster, which might not be interesting for the researcher, right? So you have those things available from R right away.
So Michelle, you mentioned some examples of using images as data for classifying protest images. Do you know some other similar examples of using computer vision to answer really interesting social science research questions?
Yes. So it's funny. I think it's an emerging community of people using the images right now. And for some reason, without talking to each other and without knowing each other, we were all working with protest. Like it seems like social movements were like a natural thing for these kind of applications and methods. But there are other interesting things. So Chris Lucas at WashU does a lot of image analysis and like speech analysis and stuff. And he, for example, is more concerned about campaigns. And he does sentiment analysis of videos of campaign ads. So that's for sure like a natural application of all of these things, right? It's more like a political marketing thing. An application that I really, really love is one from Francisco Cantu, where, well, his paper is the first paper in political science published using convolutional neural networks for images. And he had all of these images of tallies from the 1988 election in Mexico. And he basically trained a CNN to detect whether some of them were rigged or were altered in a way that was giving the dominant party back then the lead. And he trained the algorithm. I mean, the training data set include like, yeah, this is fake, where you could see that someone put like a 1 before the number, like with another pen and another color, or where you could definitely see that someone like wrote notes on top of like the others, or like censored others, other party numbers and put the highest in the winning party, etc. And then he trained an algorithm to detect how many of the total tallies were rigged. And he found a ridiculously high number. So this was the very first piece of evidence that Mexicans had. This meant a lot to Mexicans, because for a very long time, we were told that there was suspected fraud in the elections in 1988, but nobody had any proof or it was just more like anecdotal evidence. And this was the first piece of evidence that said, no, actually, yes, there were a lot of like inconsistencies there. And it's even in the Wikipedia page right now, like enumerating that evidence. So that's another example that I really, really want. Using images, but still not CNNs. Nicole Bauer at LSU has all of these content and image analysis on how feminine candidates running for election look like, and how attractiveness plays into the evaluations that you have of candidates and their likelihood of winning. A lot of it's in political communication involving how political information is shared. I focus on protest and social movements. I focus on how media, for example, depicts the caravan of migrants, like this social event, and how they are using images to talk about it, etc. Those are some examples that come to mind. I'm sorry, I always talk too much. Okay, so if there are no more questions, I think that's everything that I have for you guys. And again, I am really, really grateful, first of all, to Olga for the invitation and for hosting such an amazing event, and for all of you for coming and being interested and asking really good questions. It was a pleasure to share with you a bit of what I've known and I've done with images.
Thank you, Michelle. There's a lot of thanks and appreciations from the chat on YouTube and on Zoom. Just letting
Thank you. Oh, thank you so much. Thank you. I hope this is useful. And again, I will be happy to help further if I can do more.